Hello there, and welcome to Science for Sleep, the quiet corner of the universe where curiosity slows down, questions unfold gently, and science takes its time so you can take yours. Tonight, we're going to wander far beyond the familiar planets, past the bright paths of Jupiter and Saturn, beyond the distant blue hush of Neptune, and into a region of space where sunlight is faint. Movement is slow, and mysteries linger for decades before anyone even notices them. Our gentle question for this evening is a curious one, and perhaps a slightly haunting one in the best possible way. Is there another world out there, circling the sun in darkness, so distant and so dim that no telescope has ever seen it directly? A planet that might be many times larger than Earth, gliding silently in the outer reaches of our own solar system, hidden not because it is small, but because it is unimaginably far away. Astronomers sometimes call it Planet 9. The name itself sounds almost playful, like something from an old textbook that never quite updated itself after Pluto was reclassified. But this is not about Pluto, and it is not about nostalgia. This is about a real scientific mystery, one that researchers are still investigating right now, one that sits at the boundary between observation, mathematics, and patient imagination. Before we drift farther into that darkness together, I'd like to ask you something simple. Where are you listening from tonight? Perhaps you're in a quiet room with the lights low, or maybe there's the faint glow of a street lamp slipping through the curtains. And what time is it for you right now? Late evening perhaps, or very early morning. It's always a little comforting to remember that people all over the world are listening at different hours, each of us following our own small orbit through the day. If you find this journey soothing, or interesting, or simply a pleasant way to wind down, I'd be quietly grateful if you considered liking the video, or subscribing to the channel. It helps this gentle little space reach others who might need a calm voice at the end of a long day. And now, with that said, let's ease into our story. Most of us grow up with a picture of the solar system that feels tidy and complete. There is the sun in the centre, bright and dependable. Then come the inner planets, small and rocky, moving quickly in their tight orbits. Farther out, the giant planets drift in wider circles surrounded by rings and moons, and beyond them, a cold frontier of icy objects stretches into darkness. It feels finished, doesn't it? Like a map with clear borders, like a story whose ending has already been written. But the truth is that the solar system is far larger and far less explored than that familiar diagram suggests. Neptune, the outermost known major planet, orbits the Sun at an average distance of about 30 times the distance between Earth and the Sun. That distance is already so immense that sunlight there is faint, only a tiny fraction of what reaches us here. Yet Neptune is not the edge. Far beyond Neptune lies a vast region called the Kuiper Belt, a scattered population of icy worlds, fragments left over from the formation of the planets. Pluto lives there, along with many other dwarf planets and countless smaller bodies. And beyond even that lies another region, more distant still, called the scattered disk, where objects travel in elongated, tilted orbits that can take thousands of years to complete. This is not empty space, it is a wilderness. And wilderness, as we know from Earth, often hides things. The idea that another large planet might exist out there did not appear overnight. It emerged slowly, like a shape in fog, hinted at by small clues that did not quite make sense on their own. Astronomers began noticing that certain distant objects in the outer solar system had orbits that were strangely similar to one another. These were not planets, but small icy bodies, some only a few hundred kilometers across. Yet their paths around the Sun seemed to cluster in ways that were difficult to explain. Imagine scattering a handful of leaves into a pond. You might expect them to drift randomly. But what if instead they all slowly gathered along the same invisible line, circling in similar patterns, as though something beneath the surface were gently guiding them? That is roughly what astronomers saw. At first it was just a curiosity, perhaps coincidence, After all, the outer solar system is vast and observations are limited. It is easy to see patterns where none exist, but the more objects they discovered, the harder it became to ignore the pattern. The orbits were not just similar. They were aligned in a way that suggested the gravitational influence of something massive, something distant, something that could not yet be seen. Gravity, after all, has a way of revealing things long before light does. We have seen this before in astronomy. Neptune itself was discovered not by looking for it, but by noticing its effect on Uranus. Mathematicians calculated that an unseen planet must be tugging gently on Uranus's orbit. Telescopes were pointed to the predicted position, and there it was, exactly where the equation said it should be. In that sense, Planet 9, if it exists, would not be the first world discovered by mathematics before observation. It would simply be the most distant one. But distance changes everything. Light from the sun grows weaker with every kilometre. A planet 10 times farther from the sun does not merely receive 10 times less sunlight, it receives 100 times less. At the distances being proposed for Planet 9, the sun would appear only as a bright star, casting barely enough light to illuminate the surface. Such a world would be cold beyond ordinary imagination. Not just winter cold, not even Antarctic winter cold, but temperatures so low that common gases freeze solid, where sunlight is more memory than warmth. And yet, even in that darkness, gravity would still work. The planet would still move, slowly tracing an orbit that might take 10,000 years to complete. 10,000 years! It is a strange thing to think about, isn't it? A year so long that entire civilizations could rise and fall between one spring and the next. As we consider this possibility, it helps to remember that our understanding of the solar system has always evolved. For most of human history, we did not know that Uranus or Neptune existed. They were too dim to be recognized as planets with the naked eye. To ancient observers, the solar system ended with Saturn. Then telescopes improved and the map expanded. Later, astronomers discovered Pluto, and for decades it was considered the 9th planet. School children memorized its name, and artists imagined its icy plains and distant moons. Then, in the early 2000s, new discoveries revealed that Pluto was not alone. There were many objects of similar size in the Kuiper Belt, and the definition of a planet was reconsidered. Pluto did not disappear, of course. It is still there, still fascinating, still a world in its own right. But the solar system once again became a place of shifting boundaries, and now perhaps those boundaries are shifting again. The hypothesis of Planet 9 does not come from a single observation, but from a combination of orbital patterns, simulations, and careful statistical analysis. Researchers have modelled what kind of object could produce the clustering that is observed. Again and again, the answer points to a planet perhaps 5 to 10 times the mass of Earth, orbiting hundreds of times farther from the Sun than our own planet does. A super-Earth, in a sense. A type of planet that appears to be common around other stars, yet strangely absent in our own solar system, at least in the regions we've explored. If Planet 9 exists, it might help explain that absence. Perhaps our solar system does have such a world after all, simply hiding in the darkness, moving so slowly and reflecting so little light that it has escaped detection for decades. Finding it, however, is not easy. The sky is enormous. Even modern telescopes, powerful as they are, can only survey small portions of it at a time. A distant planet would move very slowly against the background stars, so slowly that months or even years might pass before its motion becomes noticeable. And there is another challenge. At such distances, the planet would be extremely faint, not invisible but barely distinguishable from countless distant stars and galaxies. Searching for Planet 9 is a bit like looking for a dim ember in a field of glitter, knowing only that the ember should be somewhere beyond the horizon. Still, astronomers continue the search. New surveys scan the sky, new telescopes come online, and with each passing year, the map of the outer solar system becomes a little more detailed. It is a patient kind of science, the kind that unfolds over decades, sometimes generations. kind that reminds us how vast the universe truly is and how small our corner of it remains. There is something calming about that, in a way. The realization that there are still mysteries close to home, still questions waiting quietly in the dark, still discoveries that have not yet been made. For a long time, the solar system seemed like a place we understood completely, almost comfortably so. If you opened a textbook, the picture looked neat and reassuring. The sun sat in the centre, and around it circled the planets in orderly paths, each one following its lane like a patient traveller on a quiet road. Mercury, Venus, Earth, and Mars formed the inner group, small and rocky. Beyond them stretched the realm of the giants, Jupiter with its swirling storms, Saturn with its rings, then Uranus and Neptune, cold and distant but still clearly part of the family. It felt complete, like a finished puzzle where every piece had been found and fitted into place. That sense of completeness shaped how many people imagined the solar system for generations. The orbit seemed stable, predictable, and mapped. Astronomers could calculate positions years in advance. Spacecraft could be guided across billions of kilometers with extraordinary precision. It gave the impression that the solar system was not only known, but settled, almost domesticated in a cosmic sense. Yet that impression depended on where you looked. Most of what we learned early on came from observing the brighter, closer objects, the ones that reflected enough sunlight to be easily visible. Mercury flashes briefly in twilight. Venus shines brilliantly. Mars glows with its steady reddish light. Jupiter and Saturn dominate the night sky when they rise. Even Uranus, though faint, was eventually spotted because it moved just enough to reveal itself against the stars. Neptune, discovered in 1846, was already a triumph of mathematics and observation combined. Its existence had been predicted because Uranus's orbit behaved in a way that suggested another planet was pulling on it. Astronomers calculated where such a planet should be, pointed their telescopes, and found Neptune almost exactly where expected. That success gave scientists a powerful sense of confidence. If something large existed in the solar system, surely its gravitational effects or reflected light would reveal it sooner or later. For a while, that assumption seemed reasonable. In the early 20th century, astronomers began searching for another planet beyond Neptune, often called Planet X. The search was motivated partly by small irregularities in planetary motions, and partly by the lingering sense that the solar system might not end so abruptly. The American astronomer Clyde Tombaugh eventually discovered Pluto in 1930 after painstakingly comparing photographic plates, looking for a tiny dot that shifted slightly from night to night. At the time, Pluto was celebrated as the long-sought ninth planet. Its discovery captured the imagination of the public, and for decades it held its place in the planetary lineup. School children memorized its name. Illustrations of the solar system always ended with Pluto, a small but respectable world at the edge of the sun's domain. But Pluto turned out to be much smaller than anyone expected. Estimates of its mass shrank as observations improved. It became clear that Pluto was not responsible for the orbital irregularities that had inspired the search for Planet X in the first place. Those irregularities were eventually traced to measurement errors rather than the pull of an unseen giant. For a time, it seemed the story had ended there. Pluto was not a massive outer planet, just a small icy body in a distant orbit. And beyond Pluto, there appeared to be nothing of comparable size. But appearances can be misleading, especially in astronomy, where distance dims everything and time moves at a slower pace than we're used to in daily life. The late 20th century brought better telescopes, more sensitive detectors, and new ways of surveying the sky. Slowly, astronomers began discovering other icy objects beyond Neptune. At first there were only a few, but the numbers grew. These objects formed a broad region now known as the Kuiper Belt, a disk of frozen remnants left over from the formation of the planets. This discovery changed our understanding of the outer solar system in a profound way. Pluto was no longer an isolated oddity. It was part of a larger population, one member of a distant, cold family of worlds. Some of these objects were surprisingly large. Eris, discovered in 2005, turned out to be nearly the same size as Pluto, and slightly more massive. Other dwarf planets followed, Haumea, Makemake, and several more candidates still being studied. The solar system was beginning to look less like a tidy arrangement of a few planets, and more like a complex structure with layers and regions extending far beyond the familiar orbits. That realization led to a difficult decision. In 2006, the International Astronomical Union redefined the term planet, creating a new category called dwarf planet. Pluto, along with Eris and several others, was placed in this category. The number of recognized major planets dropped from 9 to 8. For many people, this felt like a loss, as though something had been taken away. But scientifically, it was a sign of progress. The solar system was not shrinking, it was expanding in complexity. We were learning that the outer regions were populated by many objects, some large, many small, all moving in intricate and sometimes surprising patterns. And yet, even as the Kuiper Belt became better understood, new mysteries began to emerge. One of the most interesting aspects of these distant objects is how slowly they move. A body orbiting far beyond Neptune may take hundreds or even thousands of years to complete a single journey around the Sun. From our perspective, observing for a few decades is like watching only a tiny fraction of its path. That makes it difficult to determine orbits precisely. It also means that patterns can remain hidden for a long time, only becoming apparent as more observations accumulate. Astronomers began to notice that some of the most distant objects did not behave randomly. Their orbits seemed to share certain features. The points at which they came closest to the Sun, the directions of their elongated paths, and the tilts of their orbits showed similarities that were statistically unlikely to occur by chance alone. At first, these similarities were subtle, easy to overlook, but as more objects were discovered and tracked, the pattern grew clearer. This is where the sense of a fully known solar system began to shift again. It is worth pausing here to consider how extraordinary it is that such conclusions can be drawn at all. The outer solar system is unimaginably distant. Even the largest telescopes see these objects as faint points of light. No surface details, no colours, no clouds or rings. Just tiny specks moving slowly against the background stars. And yet, by measuring those motions carefully, astronomers can reconstruct the shape of entire orbits, calculate masses, simulate gravitational interactions, and infer the presence of unseen objects. It is a quiet kind of detective work, one that unfolds over years and sometimes lifetimes. Another important factor in understanding the solar system is the way it formed. About 4.6 billion years ago, the Sun and planets emerged from a rotating disk of gas and dust. In the inner regions, where temperatures were high, only metals and rocky materials could condense. Farther out, beyond what is called the frost line, ices could form, allowing planets to grow much larger by accumulating frozen water, methane, and ammonia. This is why the giant planets formed in the outer solar system. They gathered vast envelopes of gas and ice, becoming enormous compared to the rocky worlds closer to the Sun. But the process was not perfectly orderly. Young planets migrated, scattering smaller bodies, reshaping the disk and leaving behind regions filled with debris. Some objects were flung outward into distant orbits, others collided or were ejected entirely. The solar system we see today is the result of that long and chaotic history, a history that may still hold clues to the existence of unseen worlds. There is also another perspective that has influenced modern astronomy. Over the past few decades, astronomers have discovered thousands of planets around other stars, known as exoplanets. Many of these planetary systems look very different from our own. Some have giant planets orbiting extremely close to their stars. Others have multiple super-Earths in compact configurations. One striking discovery is that planets between the size of Earth and Neptune, often called super-Earths or mini-Neptunes, appear to be very common in the galaxy. Yet our solar system seems to lack such a planet in its inner regions. This raises an interesting question. Did our solar system never form such a world? Or could one exist far beyond Neptune, where we have not yet found it? That question alone does not prove the existence of Planet 9, but it makes the idea less implausible. The universe is full of surprises, and planetary systems are more diverse than anyone imagined a century ago. Meanwhile, technology continues to improve. Modern surveys use digital detectors that can scan large portions of the sky repeatedly, looking for faint moving objects. Computers analyze enormous data sets, identifying tiny shifts in position that would have been impossible to detect by eye. Even so, the search remains challenging. The farther from the Sun an object lies, the dimmer it appears. A planet hundreds of astronomical units away would reflect very little sunlight, making it difficult to distinguish from distant stars. And yet, the absence of evidence is not always evidence of absence. Sometimes it simply means we have not looked long enough, or carefully enough, or with instruments sensitive enough to reveal what is there. As our understanding of the solar system has grown, it has become clear that the outer regions are not empty, but rich and complex. They contain dwarf planets, icy bodies, and vast populations of objects still being catalogued and studied. The map continues to expand, and with each expansion comes the possibility that something larger may still be waiting to be found. This realization changes the way we think about the solar system. Instead of a closed, finished system, it becomes an open landscape, one that extends far beyond the boundaries once drawn in textbooks. And in that open landscape, the possibility of a hidden planet no longer seems so extraordinary. It becomes one more question among many, one more thread to follow in the quiet, patient work of understanding our cosmic neighbourhood. The story of Planet 9 does not begin with telescopes pointed at a specific spot in the sky. It begins with patterns, with subtle gravitational hints, with objects whose paths suggest that something unseen may be guiding them. Long before anyone seriously suggested that a hidden planet might be circling far beyond Neptune, astronomers were already studying the outermost reaches of the solar system with a kind of quiet patience that astronomy often requires. These distant regions do not reveal their secrets quickly. Objects move slowly there, sunlight is faint, and discoveries tend to arrive one at a time, years apart, like distant echoes rather than sudden revelations. The first hints of something unusual did not appear dramatic. There was no single night when a telescope revealed a massive unseen world, or when calculations suddenly produced an unmistakable answer. Instead, the story began with small, subtle irregularities, patterns that only became visible after decades of observation and careful measurement. To understand what those patterns were, it helps to picture the outer solar system not as empty space, but as a vast, sparsely populated frontier. Beyond Neptune lies a region filled with icy bodies, remnants from the early formation of the planets. Some follow relatively stable circular paths, others travel on long stretched-out orbits that carry them far from the Sun and then back again over thousands of years. Astronomers call some of these objects trans-Neptunian objects, a name that simply means they orbit beyond Neptune. Among them is a special group known as extreme trans-Neptunian objects, or ETNOs, whose orbits are particularly large and elongated. These are the objects that first drew attention, because their behaviour did not quite match expectations. Normally, if you imagine many small bodies orbiting a star, you would expect their paths to be oriented in random directions. Some orbits would tilt one way, some another. Some would stretch in one direction, others in completely different directions. Over billions of years, gravitational interactions tend to scatter objects into a wide variety of orientations. But when astronomers began examining the orbits of certain distant objects in detail, they noticed something curious. Several of these bodies seemed to cluster in the same general orientation. Their elongated orbits pointed in roughly similar directions, as though something were gently shepherding them into alignment. At first, this might not sound very surprising. After all, small number statistics can be misleading. If you observe only a handful of objects, coincidences are bound to happen. But as more observations accumulated, the clustering persisted. It became harder to dismiss as chance alone. Imagine placing a number of spinning tops on a large table and expecting them to wobble in every possible direction. But instead, many of them leaned slightly the same way, as though the table itself were tilted in a subtle but consistent manner. You might begin to suspect that something beneath the surface is influencing their motion. That is roughly how astronomers began to think about these distant objects. The key idea was gravity. Gravity is an extraordinarily patient force. It does not need to be strong to have an effect. Given enough time, even a gentle gravitational pull can reshape orbits, nudging objects into new configurations. In the outer solar system, where orbital periods stretch into centuries or millennia, these slow influences can accumulate over vast spans of time. Researchers began running computer simulations to see what might produce the observed clustering. They modelled the known planets, the gravitational effects of the Sun, and the interactions among the small bodies themselves. Yet in many of these simulations, the clustering did not persist. The orbits tended to spread out randomly over time. Something appeared to be missing from the picture. Then came an intriguing possibility. What if there were another massive object far beyond Neptune, one large enough to influence these distant bodies but too far away and too dim to have been detected directly? When astronomers added such a hypothetical planet to their simulations, something remarkable happened. The clustering of orbits could be reproduced. A distant planet, several times the mass of Earth, travelling on a highly elongated orbit hundreds of astronomical units from the Sun, could gravitationally shepherd the smaller objects into the patterns that were being observed. This was not proof, of course. It was only a possible explanation, but it was a compelling one. The idea gained wider attention in 2016, when astronomers Konstantin Batygin and Michael Brown published a study analysing the orbits of several extreme trans-Neptunian objects. Their work suggested that the observed clustering was unlikely to be random and could be explained by the presence of a previously unknown planet. Michael Brown, incidentally, is sometimes known informally as the astronomer who demoted Pluto, because of his role in discovering large Kuiper Belt objects that led to Pluto's reclassification. There is a quiet irony in the possibility that the same researcher might also be involved in the discovery of a new distant planet. But again, this was not a discovery in the traditional sense. No telescope had seen Planet 9, no image existed. There was only the evidence of its possible gravitational influence, inferred indirectly from the motions of smaller bodies. This kind of reasoning has a long history in astronomy. Neptune itself was discovered in much the same way, predicted from irregularities in Uranus's orbit before it was ever observed. In that case, the prediction proved correct, and the planet was found almost exactly where calculations indicated it should be. Yet history also offers cautionary tales. The search for the hypothetical planet Vulcan in the 19th century, proposed to explain irregularities in Mercury's orbit, ultimately failed. The anomalies were eventually explained not by another planet, but by Einstein's theory of general relativity. So astronomers approached the Planet 9 hypothesis with a mixture of excitement and caution. The evidence is intriguing, but not definitive. Alternative explanations remain possible, and observations are still incomplete. One of the challenges in studying these distant objects is that they are extremely faint and difficult to detect. Surveys of the outer solar system are influenced by observational biases. Telescopes tend to search certain regions of the sky more than others, and objects are easier to detect when they are closer to the Sun and brighter. This means that the sample of known objects may not represent the true distribution. Some researchers have argued that the apparent clustering might be partly due to these observational biases. If telescopes are more likely to discover objects in certain regions, the data could give the illusion of alignment even if none exists. This debate is ongoing, and it is a healthy part of the scientific process. Hypotheses are proposed, challenged, tested, and refined. Over time, evidence accumulates, and a clearer picture begins to emerge. Meanwhile, additional distant objects continue to be discovered, and many of them seem to support the idea that something unusual is happening in the outer solar system. Some objects have orbits that are tilted at steep angles, even nearly perpendicular to the plane in which most planets orbit. Simulations suggest that a distant massive planet could produce such effects, scattering some bodies into highly inclined orbits while shepherding others into clusters. Another intriguing clue comes from objects whose orbits keep them unusually far from Neptune. Normally, Neptune's gravity would be expected to perturb and scatter objects that venture too close, yet some distant bodies maintain stable orbits that avoid strong interactions with Neptune, as though another gravitational influence were helping to shape their paths. It's important to remember that these effects are subtle. Nothing is being violently pulled or dramatically altered. The outer solar system is a quiet place, and its mysteries reveal themselves slowly, through careful measurement and long-term observation. There is something almost meditative about this kind of science. Astronomers gather data year after year, refining orbital calculations, improving models, and patiently waiting for patterns to become clear. The timescales involved are so long that a single human lifetime covers only a tiny fraction of many of these objects' orbits, and yet, even within those limits, meaningful insights can emerge. If Planet 9 exists, it is likely travelling on an orbit so vast that it spends most of its time far from the Sun, moving slowly through deep darkness. Only occasionally would it approach the inner part of its orbit, becoming slightly brighter and easier to detect. At present, it may simply be in a region of the sky that has not yet been surveyed deeply enough, or where its faint light blends into the background of distant stars. The search continues, driven by new telescopes and new surveys designed to map the sky more thoroughly than ever before. Instruments like the Vera C. Rubin Observatory, which is expected to conduct an unprecedented survey of the night sky, may provide new data that could confirm or refute the existence of Planet 9. Until then, the evidence remains indirect, a collection of gravitational whispers rather than a clear visual signal. There is a quiet beauty in that idea, the notion that something large and distant might reveal itself not by shining brightly, but by the gentle influence it exerts on its surroundings. Gravity leaves traces, patterns in motion, subtle signatures that can be read by those who know how to look. And as astronomers continue to study those signatures, refining their models and searching the sky, the question remains open, patient, and unresolved. Something curious began to stand out as astronomers continued to catalogue distant objects beyond Neptune, and it was not the objects themselves that first drew attention, but the shapes of the paths they followed. In astronomy, an orbit is like a fingerprint. It carries information about where an object formed, what it has encountered, and what forces have influenced it over time. Most orbits in the solar system, especially among the planets, are fairly well behaved. They are nearly circular, lie close to the same flat plane, and follow patterns that can be predicted with remarkable precision. But far beyond Neptune, that orderly picture begins to loosen. Many distant bodies follow elongated paths that stretch far from the Sun before looping back inward. That alone is not surprising. Gravitational interactions with the giant planets can scatter smaller objects into stretched orbits, sometimes sending them outward for millions of years. Astronomers have long known about comets that behave this way, appearing briefly in the inner solar system before vanishing again into distant darkness. What began to puzzle researchers was not that some distant objects had elongated orbits, but that certain ones seemed to share similar orientations in space. Their closest approaches to the Sun, their directions of travel, and even the tilts of their orbital planes showed patterns that did not look random. To appreciate why this was unusual, it helps to imagine how orbits normally evolve. Picture a large open field with many spinning wheels rolling across it in different directions. If there is no guiding force, you would expect the wheels to scatter, each one heading its own way. Over time, their paths would become increasingly mixed, leaving no clear pattern behind. Gravity, of course, can act as a guiding force, but in the outer solar system, the known planets are too far away to strongly organize the motions of objects that travel hundreds of astronomical units from the Sun. Neptune exerts some influence, certainly, but its reach is limited. Objects that wander far beyond Neptune's orbit should, in theory, be influenced only weakly by the planets we know, and yet some of these objects seem to be moving as though something else were quietly shaping their paths. One of the key measurements astronomers examine is called the argument of perihelion, which describes the orientation of an orbit's closest point to the Sun. If you mapped many distant objects and found that their closest approaches occurred in every possible direction, that would suggest randomness. But if many of them cluster in similar directions, it hints at a shared influence. That is precisely what researchers began to notice. Several extreme trans-Neptunian objects had arguments of perihelion that were not scattered randomly, but clustered within a relatively narrow range. At first, this observation was tentative. The number of known objects was small, and small samples can be misleading. But as years passed and more objects were discovered, the clustering did not disappear. In fact, it became more difficult to ignore. Another unusual feature involved the long axes of their orbits. These elongated paths seemed to point in similar directions through space, as though the objects were all avoiding a particular region or being guided along preferred routes. Astronomers began to ask themselves a simple question: what kind of gravitational influence could maintain such patterns over billions of years? Simulations provided an important clue. When researchers modelled the outer solar system without any additional massive body, the clustered orbits tended to disperse over time. Gravitational interactions, even weak ones, gradually scrambled the orientations, erasing the pattern. But when a distant, massive planet was added to the simulations, something different happened. The clustering could persist. The hypothetical planet acted like a distant shepherd, its gravity gently nudging smaller objects into stable configurations that maintained their alignment. This effect did not require violent interactions or close encounters. It worked slowly, over millions of years, through a process known as secular perturbation. In simple terms, this means that a gravitational influence can gradually alter an orbit's orientation without dramatically changing its size or shape. It is a subtle process, but over long timescales, subtle processes can produce dramatic results. There was another piece of the puzzle that made the situation even more intriguing. Some distant objects were found on highly inclined orbits, tilted steeply relative to the plane in which most planets orbit. A few even travelled on paths that were almost perpendicular to that plane. Such extreme tilts are difficult to produce through interactions with the known planets alone. Simulations suggested that a distant massive body could scatter objects into these unusual orientations, creating a population of high inclination orbits that matched what astronomers were beginning to observe. The more data accumulated, the more the hypothesis of an unseen planet seemed capable of explaining multiple features at once: the clustering of perihelia, the alignment of orbital axes, and the existence of highly tilted orbits. Still, caution remained essential. Astronomy has seen apparent patterns before that later turned out to be statistical illusions. Observational bias is a persistent challenge, especially when studying faint objects at the limits of detection. Telescopes do not survey the sky uniformly. Some regions are observed more frequently, and objects are easier to detect when they are closer to the Sun, or located in areas where background stars are less dense. These factors can influence which objects are discovered and which remain unseen. If discoveries are biased towards certain regions of the sky, apparent clustering could arise even if the true distribution were random. Researchers work carefully to account for these biases, analysing survey methods and detection probabilities. Some studies concluded that the clustering remained significant even after accounting for observational effects, while others argued that the evidence was still inconclusive. This debate continues, and it is a normal and healthy part of science. Hypotheses are tested, challenged, and refined, sometimes over many years. Meanwhile, new discoveries continue to add pieces to the puzzle. One particularly intriguing object, known as Sedna, follows an orbit that carries it far beyond the Kuiper Belt, with a perihelion so distant that Neptune's gravity cannot easily explain its trajectory. Sedna and similar objects form a group sometimes called the inner Oort cloud objects, bodies that occupy a transitional region between the Kuiper Belt and the distant spherical halo of comets known as the Oort cloud. The origins of such objects remain uncertain. Some astronomers suggest that they were influenced by passing stars in the Sun's birth cluster billions of years ago. Others propose that a distant planet could have played a role in shaping their orbits. It is possible that multiple mechanisms are involved. The outer solar system is a complex environment shaped by the combined effects of planetary migration, stellar encounters, and long-term gravitational interactions. Another curious feature of some extreme trans-Neptunian objects is that their orbits keep them far from Neptune at all times. This is unusual because Neptune's gravity tends to scatter objects that venture too close. The existence of stable orbits that avoid Neptune suggests that some additional influence may be helping to maintain those paths. Simulations again provided a possible explanation. A distant planet on an elongated orbit could create regions of stability, where smaller objects are trapped in resonances, their motions synchronized in subtle ways that prevent close encounters with Neptune. Resonance is a fascinating phenomenon. It occurs when two orbiting bodies have periods that form simple ratios, such as 2:1 or 3:2. Over time, these repeating gravitational interactions can lock objects into stable configurations. Jupiter, for example, maintains resonant relationships with several groups of asteroids, shaping the structure of the asteroid belt. If a distant planet were present, it could create similar resonant structures in the outer solar system, organizing the motions of smaller bodies in ways that would otherwise be difficult to explain. All of this evidence, taken together, does not prove that Planet 9 exists, but it does suggest that the outer solar system may be influenced by something more than the planets we already know. It is also worth considering how difficult it would be to detect such a planet directly. At distances of several hundred astronomical units, even a large planet would reflect very little sunlight. Its apparent brightness could be thousands of times fainter than Neptune's, making it extremely challenging to spot. Moreover, its motion across the sky would be slow, almost imperceptible over short periods. Detecting it would require careful comparison of images taken months or even years apart, looking for a tiny shift against the background stars. This kind of search demands patience and persistence. It is not the sort of discovery that happens overnight. There is something quietly remarkable about the fact that we can infer the possible existence of a world we have never seen, simply by studying the motions of distant specks of light. It speaks to the power of physics and mathematics, and to the patience of the people who devote their lives to understanding the cosmos. At the same time, it reminds us that our knowledge of the solar system is still incomplete. Even in our own cosmic neighbourhood, mysteries remain, waiting to be unravelled. As astronomers continue to study these unusual orbits, they refine their models and search for additional objects that might confirm or challenge the patterns already observed. Each new discovery adds another data point, another clue, another small piece of a much larger puzzle. And as those clues accumulate, the question grows more compelling. If these distant bodies are being guided, if their orbits truly are being shaped by an unseen influence, then what kind of world could be responsible? How large would it have to be? How far away, and what might such a planet be like in the deep, cold darkness beyond Neptune? If you pause for a moment and think about it, The idea of detecting something without ever seeing it directly is not as strange as it first sounds. In everyday life, we do it constantly. You can feel the warmth of sunlight on your skin before you look up at the sky. You can hear footsteps in another room and know someone is there long before you see them. The presence is inferred from its effects. Astronomy often works in much the same way. In fact, many of the most important discoveries in the history of science began not with images, but with subtle influences, small deviations, gentle tugs that hinted at something hidden. Gravity in particular is very good at revealing what cannot yet be seen. Every object with mass exerts a gravitational pull, no matter how distant or faint it may be. That pull may be weak, almost imperceptible, but over long periods of time, it leaves traces in the motions of other bodies. Orbits shift. Paths bend slightly. Patterns emerge that should not exist if only the known objects were present. This is why astronomers sometimes speak of feeling a planet before seeing it. Not literally, of course, but in the sense that its gravitational presence becomes evident in the behavior of other objects long before any telescope captures a picture. Neptune was discovered this way, so were many exoplanets orbiting distant stars. In those cases, astronomers observed tiny wobbles in the motion of a star, caused by the gravitational pull of an unseen planet. The planet itself was invisible at first, lost in the glare of its star, but its influence gave it away. Planet 9, if it exists, would be another example of this principle, though on a far grander scale and at a much greater distance. The evidence does not come from a single orbit or a single object. It comes from a collection of distant bodies whose motions, taken together, seem to point toward a common explanation. It is like noticing that leaves on a pond are drifting in similar patterns and realizing that a slow, unseen current must be guiding them. What makes this case especially intriguing is the scale involved. The hypothetical Planet 9 is thought to be several times more massive than Earth, perhaps similar in size to Uranus or Neptune, though likely smaller than those giants. That is not a tiny world hiding in darkness. That is a substantial planet, one that would dominate its region of space, shaping the motions of smaller bodies over vast distances. And yet, despite its size, it could remain unseen simply because of how far away it might be. To understand this, it helps to think about light and distance. The brightness of an object illuminated by the sun depends on two things: how much sunlight reaches it, and how much of that light reflects back toward us. Both of these factors decrease dramatically with distance. If a planet were 10 times farther from the sun than Earth, it would receive only 1/100th as much sunlight. If it were 100 times farther away, the sunlight would be 10,000 times weaker, and the reflected light would have to travel all the way back to Earth, growing fainter still. By the time you reach distances of several hundred astronomical units, a planet that might appear bright and colourful up close becomes a faint, cold point of light, barely distinguishable from distant stars. There is another factor as well. Objects that far from the sun move very slowly across the sky. From our perspective, their motion may be so gradual that it takes months or even years to detect. Most surveys of the sky are designed to find objects that move more quickly, such as asteroids or nearer trans-Neptunian objects. A planet moving at a glacial pace could easily slip through unnoticed, so the absence of direct observation does not necessarily mean absence of existence. It may simply mean that the object is faint, slow, and located in a part of the sky that has not yet been searched deeply enough. This is why astronomers rely so heavily on indirect evidence. They look for gravitational fingerprints, patterns in orbital behavior that cannot be explained by known influences alone. One of the most compelling aspects of the Planet 9 hypothesis is that it explains several different observations at once. The clustering of distant orbits, the existence of highly inclined objects, and the presence of bodies that remain far from Neptune all fit naturally into simulations that include a distant massive planet. It is as though multiple clues, scattered across the outer solar system, all point toward the same invisible source. Of course, there are other possible explanations. Some scientists have suggested that the clustering might be caused by collective gravitational effects among many smaller bodies rather than a single large planet. Others propose that observational biases could still be influencing the data in subtle ways. These are important considerations, and they are taken seriously. Science moves forward by testing ideas from every angle, looking for weaknesses, refining models, and gathering more evidence. But even with these uncertainties, the possibility of Planet 9 remains compelling, partly because it fits into a broader understanding of how planetary systems form. When astronomers study other stars, they often find planets that are larger than Earth, but smaller than Neptune, worlds sometimes called super-Earths or mini-Neptunes. These planets appear to be common, perhaps even the most common type of planet in the galaxy, and yet our solar system seems to lack such a world in its inner regions. Mercury, Venus, Earth, and Mars are all smaller than Earth, or only slightly larger. Beyond them come the gas giants, with a large gap in size between Earth and Neptune. This absence has puzzled astronomers for years. Why does our solar system seem to be missing a type of planet that appears so frequently elsewhere? One possibility is that such a planet did form here, but was later scattered outward during the early chaotic period when the giant planets were migrating. In this scenario, interactions among Jupiter, Saturn, Uranus, and Neptune could have flung a fifth large planet into a distant orbit, where it remains today, circling the Sun slowly and silently. Computer simulations of planetary formation sometimes produce results like this. In some models, additional planets are ejected entirely, becoming rogue planets drifting between the stars. In others, a planet remains gravitationally bound to its star, but is pushed into a distant, elongated orbit. If Planet 9 exists, it might be a survivor of that early period, a relic of a time when the solar system was far more crowded and chaotic than it is now. Imagining such a world invites a different way of thinking about the solar system. Instead of a compact family of planets clustered near the Sun, we begin to see it as a vast system extending far into darkness, with distant members that move on timescales far beyond a human lifetime. A year on such a planet might last 10,000 Earth years or more. Seasons, if they exist at all, would change so slowly that no civilization could observe a full cycle. The Sun would appear as a brilliant star, bright enough to cast faint shadows but not to warm the surface significantly. Temperatures would be extremely low, perhaps only a few dozen degrees above absolute zero. Any atmosphere would be thin or frozen. The landscape, if we could see it, might be covered in ices of methane, nitrogen, or carbon monoxide, substances that are gases on Earth but solids in such cold conditions. And yet, even in such a remote environment, the laws of physics remain the same. Gravity shapes orbits. Heat flows slowly outward from planetary interiors. Chemical processes continue, albeit at a glacial pace. It is a quiet kind of existence, far removed from the warmth and activity of the inner solar system, but not devoid of interest or complexity. There is something humbling about the idea that such a world could exist within our own solar system, not in some distant galaxy, but in our cosmic backyard, unseen yet exerting a measurable influence. It reminds us that exploration is not finished, that even familiar territory can hold surprises, that maps can still have blank regions waiting to be filled. Astronomers continue to search, using telescopes that scan wide areas of the sky, looking for faint moving points of light. The Vera C. Rubin Observatory, for example, is expected to detect vast numbers of distant objects, potentially providing the data needed to confirm or rule out the existence of Planet 9. Until then, the evidence remains indirect, a story told through gravitational interactions rather than images, and perhaps that makes the mystery all the more intriguing. There is a certain quiet elegance in discovering a world not by seeing it directly, but by noticing the gentle ways it shapes its surroundings, the subtle signatures it leaves in the motions of distant bodies. If a hidden planet is influencing these objects, where exactly is it? What region of the sky might it occupy, and how do astronomers narrow down a search across such an immense expanse of space? Far beyond the orbit of Neptune, past the region where the giant planets circle in predictable paths, the solar system begins to change character. The familiar structure of widely spaced planets gives way to something looser, more scattered, and far quieter. This is the Kuiper Belt, a vast population of icy bodies stretching outward in a broad ring, and for a long time it remained almost completely unknown. If you had asked an astronomer in the early 20th century what lay beyond Neptune, the answer would likely have been simple. Pluto, perhaps, and then empty space, a slow fading into the distant darkness that eventually merges with the realm of comets. That picture seemed reasonable, because telescopes had not revealed anything more. But absence of evidence, especially in astronomy, often means only that something is faint, distant, or difficult to detect. The Kuiper Belt is all three. The story of its discovery unfolded gradually, and like many scientific discoveries, it began with a prediction long before any direct observation. In 1951, an astronomer named Gerard Kuiper suggested that remnants from the formation of the solar system might exist beyond Neptune. He imagined a region filled with small icy bodies, leftovers that never merged into planets. At the time, this idea was largely theoretical. No one had seen such a belt, and detecting small, dark objects at those distances seemed nearly impossible. Decades passed before technology caught up with the theory. In 1992, astronomers David Jewett and Jane Liu discovered the first confirmed Kuiper Belt object beyond Pluto, a small icy body now known as 1992 QB1. The name may not sound very poetic, but the discovery was significant. It was proof that Pluto was not alone, that the outer solar system was not empty, and that an entire population of distant worlds had been waiting quietly beyond the reach of earlier instruments. After that first detection, more objects began to appear. At first, just a handful, then dozens, then hundreds. Today, thousands of Kuiper Belt objects are known, and many more are believed to exist, perhaps millions, ranging in size from small chunks of ice to dwarf planets, hundreds or even thousands of kilometers across. It is difficult to picture the scale of this region. The Kuiper Belt begins roughly at Neptune's orbit, around 30 astronomical units from the Sun, and extends outward to about 50 astronomical units or more. One astronomical unit, of course, is the distance between Earth and the Sun, about 150 million kilometers. So even the inner edge of the Kuiper Belt lies billions of kilometers away in a realm where sunlight is faint and temperatures are extremely low. Despite its enormous extent, the Kuiper Belt is not densely packed. If you could somehow travel through it in a spacecraft, you would not see a crowded field of icy bodies drifting past your window. The objects are separated by vast distances, often millions of kilometers apart. It is more like a sparse archipelago than a dense swarm. Still, the Kuiper Belt is important because it preserves clues about the early solar system. These icy bodies formed from the same primordial disk of gas and dust that gave rise to the planets, but they remained small, never gathering enough material to grow into full-sized worlds. In a sense, they are time capsules, frozen remnants of the solar system's youth. Pluto, once thought to be a solitary outpost, is now understood as one of the largest members of this population. Its heart-shaped glacier, nitrogen ice plains and distant mountains, revealed in remarkable detail by the New Horizons spacecraft in 2015, showed that even small, distant worlds can be complex and dynamic. Pluto is not merely a frozen rock. It is a world with geology, atmosphere, and history. And Pluto is only one among many. Other dwarf planets in the Kuiper Belt, such as Eris, Haumea, and Makemake, add to the diversity of this distant frontier. Some are nearly spherical, shaped by their own gravity. Some spin rapidly, elongated by their rotation. Some have moons, and some may have thin, transient atmospheres that freeze and thaw over the course of their long orbits. These discoveries gradually changed the way astronomers think about the solar system. The outer regions were no longer empty space punctuated by a few isolated objects. They were a vast, complex environment, shaped by gravity, collisions, and the slow passage of time. The Kuiper Belt also plays another role. It is the source of many short-period comets, those icy visitors that occasionally appear in the inner solar system with glowing tails and bright comas. These comets are thought to originate in the Kuiper Belt and are nudged inward by gravitational interactions, eventually becoming visible from Earth as they approach the Sun. In that sense, the Kuiper Belt is not only a distant frontier, but also a reservoir, continually supplying new objects to the inner solar system over millions of years. As astronomers studied this region more closely, they began to classify Kuiper Belt objects into different categories based on their orbits. Some follow relatively circular paths, remaining in a stable resonance with Neptune. Pluto itself belongs to this group, completing 2 orbits around the Sun for every 3 orbits of Neptune, a gravitational dance that keeps the 2 worlds from ever colliding. Other objects have more elongated or tilted orbits, suggesting a more complex history. Some appear to have been scattered outward by gravitational interactions with Neptune in the distant past. These are known as scattered disk objects, and they can travel hundreds of astronomical units from the Sun before returning inward. It was among these scattered and extreme objects that the first hints of Planet 9 began to emerge. The Kuiper Belt is not uniform. It has structure, regions where objects cluster, gaps where few are found, and populations with distinct orbital characteristics. Much of this structure can be explained by the influence of Neptune, whose gravity shaped the belt during the early migration of the giant planets. But not all of it. Some objects orbit far beyond the main concentration of the Kuiper Belt, in paths so large and so detached from Neptune's influence that their origins are difficult to explain. Sedna is one of the most famous examples. Its orbit carries it out to nearly 1,000 astronomical units at its farthest point, and even at its closest approach to the Sun, it remains far beyond Neptune's reach. Sedna's orbit raised questions from the moment it was discovered. What could have placed it on such a distant path? A passing star in the Sun's birth cluster might have done it, or perhaps interactions with other massive bodies early in the solar system's history, or perhaps something still present in the outer solar system is influencing objects like Sedna, shaping their orbits over long periods of time. This is where the Kuiper Belt becomes directly connected to the mystery of Planet 9. The distant objects that show unusual orbital clustering are not part of the dense inner belt. They are members of its outermost fringes, bodies that travel so far from the Sun that their motions may be influenced by forces we do not yet fully understand. Studying these objects is challenging. They are faint, often barely detectable even with large telescopes. Observations must be repeated over many years to determine their orbits accurately. A single observation reveals only a tiny portion of a path that may take thousands of years to complete. It requires patience, careful measurement, and sometimes a willingness to wait for new data to arrive slowly year after year. There is something calming about this kind of work, the steady accumulation of knowledge, the quiet refinement of orbits, the gradual emergence of patterns. Astronomy often moves at this pace, measured not in days or weeks but in decades. As more distant objects were discovered and their orbits calculated, astronomers began to notice that some of them shared unusual characteristics. Their elongated paths pointed in similar directions. Their closest approaches to the Sun occurred in a narrow range of orientations. Their orbital planes showed unexpected tilts. These were not dramatic effects. No object was being violently thrown about. Instead, there was a subtle sense that something was gently guiding them, maintaining a pattern that should have dispersed long ago. The Kuiper Belt, once thought to be the quiet outer edge of the solar system, began to look more like a frontier shaped by unseen influences. Another fascinating aspect of this region is how slowly everything moves. At 50 astronomical units, the Sun's gravity is still dominant, but orbital periods stretch into centuries. At hundreds of astronomical units, they stretch into millennia. Changes that would be obvious in the inner solar system unfold almost imperceptibly here. This slow pace means that gravitational interactions can act over extraordinarily long timescales, nudging orbits little by little until the cumulative effect becomes significant. If a distant planet exists, its influence on the Kuiper Belt would not be obvious in a single orbit or a single century. It would reveal itself gradually through the long-term behavior of many objects, like a tide that reshapes a shoreline grain by grain. Understanding this region also reminds us of how small our own orbit is in comparison. Earth circles the Sun at a comfortable distance, completing a year in just 365 days. Even Neptune's long year, lasting 165 Earth years, feels brief compared to the timescales of the scattered disk and the distant fringes of the Kuiper Belt. In those regions, a single orbit may take longer than recorded human history. The Kuiper Belt is sometimes described as a frozen archive, preserving the early conditions of the solar system, but it is also a dynamic environment, slowly evolving under the influence of gravity, collisions, and the occasional perturbation from passing stars. And somewhere beyond its outer edge, perhaps far beyond, the possibility remains that a much larger object is moving silently, shaping the motions of the smaller worlds without revealing itself directly. Astronomers continue to survey the sky, searching for faint points of light that move just enough to betray their presence. Each new discovery adds another piece to the puzzle, another orbit to analyze, another clue about the structure of the outer solar system. The Kuiper Belt, once forgotten and unknown, has become one of the most important regions for understanding how our planetary system formed and how it continues to evolve. What finally drew widespread attention to the possibility of a hidden planet was not a single object, nor even a single unusual orbit, but a pattern that slowly emerged as more and more distant bodies were discovered and tracked. It was the kind of pattern that does not announce itself loudly. Instead, it becomes visible only after years of careful observation, like noticing that certain stars in the sky seem to form a shape only after you have looked at them long enough. Astronomers studying the outer solar system were already accustomed to strange orbits. Many objects beyond Neptune travel on elongated paths, and many have orbital planes tilted at different angles. The region is dynamic and complex, shaped by the migrations of the giant planets long ago. So when the first few unusual orbits were identified, no one was immediately surprised. But then the number of known distant objects began to grow, and with each new discovery the picture became slightly clearer. Some of the most distant bodies, the ones whose orbits never came close to Neptune, seemed to share something unexpected. Their orbits were not randomly oriented. Instead, they appeared to cluster in a particular way. To understand why this mattered, it helps to picture how orbits are described. An orbit is not just a loop around the Sun. It has an orientation in three-dimensional space. It has a direction in which its longest axis points. It has a tilt relative to the flat plane in which most planets orbit. And it has a point where the object comes closest to the Sun called the perihelion. If you plotted many such orbits and found that their orientations pointed in every possible direction, that would be exactly what you would expect in a system where no strong organizing influence is present. Random processes tend to produce random results. But that is not what astronomers saw. Instead, several extreme trans-Neptunian objects appear to have perihelia that pointed in roughly the same direction. Their elongated orbits seem to be aligned, as though they were all following invisible lanes carved through space. At first, this clustering involved only a handful of objects, and small numbers can be misleading. Coincidences happen. Patterns appear where none truly exist. Astronomers are well aware of this, and they are careful not to draw conclusions too quickly. So the observations continued. More objects were discovered, and their orbits were calculated with increasing precision, and the clustering remained. It was not perfect alignment, of course. Nature rarely produces perfect patterns, but the similarity was striking enough that it demanded explanation. One of the astronomers who examined this evidence closely was Michael Brown, working with his colleague Konstantin Batygin. Brown had already spent years studying distant objects in the Kuiper Belt and beyond, and he was familiar with the complexities of orbital dynamics. Together they began to investigate whether the observed clustering could arise naturally from the gravitational influence of the known planets alone. They ran simulations, modelling the outer solar system over long periods of time. These simulations included the Sun, the giant planets, and a population of small distant bodies. Over millions and billions of years, the orbits in these models tended to spread out. The clustering did not persist. That result suggested that something was missing. So they tried adding a hypothetical planet to the simulations, a planet far beyond Neptune, with a mass several times that of Earth, and an orbit that stretched hundreds of astronomical units from the Sun. The results were remarkable. With the additional planet included, the clustering of distant orbits could be maintained over long timescales. The simulated objects behaved in ways that closely resembled the real observations. It was not proof, but it was a compelling clue. There was another aspect of the clustering that made it particularly intriguing. Some of the distant objects had orbits that were not only aligned but also anti-aligned with the hypothetical planet's orbit. In other words, their elongated paths pointed in directions that would keep them far from the planet itself, avoiding close encounters. This might sound counterintuitive at first. How could a planet influence objects without pulling them toward it? The answer lies in the subtleties of orbital mechanics. Over long periods of time, gravitational interactions can create stable configurations in which objects avoid close approaches, settling into patterns that minimize disruptive encounters. It is a bit like dancers on a crowded floor finding rhythms that keep them from colliding, each one adjusting their steps in response to the others. The simulation suggested that a distant planet could act as a kind of distant conductor, shaping the orbits of smaller bodies in ways that produced the observed clustering. Still, caution was necessary. Observational bias remained a serious concern. Telescopes do not search the sky evenly. Some regions are studied more frequently than others, and objects are easier to detect when they are closer to the Sun, or located in areas where background stars are less dense. If most discoveries occurred in certain regions of the sky, it could create the illusion of clustering even if the true distribution were random. To address this possibility, researchers analysed the survey methods used to discover the objects. They examined which parts of the sky had been searched, how detection probabilities varied, and whether the clustering could be explained by observational bias alone. The results of these analyses were debated. Some studies concluded that the clustering remained statistically significant even after accounting for biases. Others argued that the sample size was still too small to be certain. This debate continues, and it is an important part of the scientific process. Extraordinary claims require careful scrutiny, and astronomers are well aware of how easily patterns can mislead. At the same time, new discoveries continue to add weight to the mystery. Additional extreme trans-Neptunian objects were found, and many of them fit the pattern. The clustering did not disappear as the sample grew larger. If anything, it became more intriguing. Another curious feature emerged as well. Some distant objects were found on highly inclined orbits, tilted steeply relative to the plane of the solar system. A few even had orbits that were nearly perpendicular to that plane. Such extreme tilts are difficult to produce through interactions with Neptune alone. Simulation suggested that a distant massive planet could scatter objects into these unusual orientations, while also maintaining the clustering of others. It was as though multiple pieces of evidence, each puzzling on its own, began to form a coherent picture when considered together. Yet the picture was still incomplete. Astronomers did not know where such a planet might be located. They did not know its exact mass or orbit. They only knew that certain patterns in the motions of distant objects seemed easier to explain if such a planet existed. there is something quietly fascinating about this kind of investigation. It is not dramatic or sudden. It unfolds slowly, through careful measurements and patient analysis, through years of observations and countless hours of simulation. It is a reminder that science often advances not through flashes of inspiration alone, but through persistence and attention to detail. The clustering mystery also highlights how much of the solar system remains unexplored. The region beyond Neptune is vast, far larger than the inner planetary system. Even with modern telescopes, only a small fraction of its objects have been discovered. There may be thousands, perhaps millions, of distant bodies whose orbits are still unknown. Each new discovery has the potential to refine our understanding, to confirm or challenge existing theories, to reveal patterns that were previously invisible. And somewhere among those faint points of light, there may be clues that bring us closer to answering the question of Planet 9. One of the most striking aspects of the clustering is how delicate it is. The gravitational influence required to maintain such patterns does not need to be overwhelming. It only needs to be consistent, acting over millions of years, gently guiding the orbits of smaller bodies. This is one of the quiet truths of celestial mechanics. Given enough time, even small forces can shape the architecture of entire systems. It is also a reminder of how interconnected everything in the solar system is. A planet hundreds of astronomical units away could influence objects that never come close to it, simply through the long, slow pull of gravity. As astronomers continue to study the clustering of distant orbits, they refine their models, testing different scenarios, adjusting parameters, and comparing the results with observations. Some models suggest that a planet with a mass between 5 and 10 times that of Earth, travelling on a highly elongated orbit, could reproduce many of the observed features. But models are not reality. They are tools, ways of exploring possibilities. The ultimate test will be observation, either the direct detection of the planet itself, or the accumulation of enough evidence to confirm or rule out its existence. For now, the clustering mystery remains one of the most intriguing puzzles in planetary science. It is a story told through motion rather than light, through patterns rather than images. And as we consider what kind of world could produce such effects, the question naturally arises: if a distant planet is shaping these orbits, how large would it need to be, how far away, and what might its long, cold journey around the Sun actually look like? Long before a telescope ever points toward a particular patch of sky, astronomy often begins somewhere quieter, in notebooks, on chalkboards, and inside computer models where numbers move long before planets do. Equations have a curious way of revealing things that no eye has yet seen. They do not show colour or texture or clouds, but they show influence. They show patterns that should not exist unless something unseen is present. That is how the idea of a hidden world in the outer solar system began to take shape, not as a photograph, not as a bright dot in an image, but as a mathematical possibility that gradually became difficult to ignore. When astronomers looked at the clustering of distant orbits, they were not just seeing a pattern. They were seeing a problem that required explanation. The known planets, even Neptune, could not easily account for the way certain extreme trans-Neptunian objects behaved. Their paths were too detached, their orientations too similar, their stability too persistent. So the next step was to ask a simple but powerful question. If there were an additional planet, what kind of planet would it need to be in order to produce these effects? Answering that question required careful modelling. Astronomers began by constructing simulations of the outer solar system, including the Sun, the giant planets, and populations of distant icy bodies. These simulations ran not for years or decades, but for millions and sometimes billions of simulated years, allowing researchers to watch how orbits evolved under different conditions. At first, they ran the models without any additional planets. Again and again, the result was similar. The distant objects did not remain clustered. Over long timescales, their orbits spread out. their orientations drifting into randomness. The patterns seen in real observations did not persist. Then researchers began experimenting. What if there were a planet far beyond Neptune? Not an enormous gas giant like Jupiter, but something smaller, perhaps several times the mass of Earth. A world large enough to exert a steady gravitational influence, but distant enough to remain faint and difficult to detect. When such a planet was introduced into the simulations, something interesting happened. Under certain conditions, the clustering of orbits remained stable. The distant objects followed paths that resembled what astronomers were actually observing. This was the moment when mathematics began to whisper rather than merely suggest. The simulations did not prove the existence of Planet 9, but they showed that such a planet could explain multiple observations at once. The next question was how to narrow down the possibilities. A planet could not be placed arbitrarily anywhere in the outer solar system. Its mass, orbit, and position would all determine how it influenced other objects. Too small, and it would have little effect. Too large, and it would produce disturbances that are not observed. Too close, and it would likely have been detected already. Too far, and its influence would be too weak. So astronomers began to explore ranges. What mass would be consistent with the data? What kind of orbit would produce the observed clustering? How elongated would that orbit need to be, and how tilted relative to the plane of the solar system? Gradually a picture began to emerge. The hypothetical planet, if it exists, is thought to have a mass roughly 5 to 10 times that of Earth. That would make it larger than any terrestrial planet in our solar system, but still much smaller than Uranus or Neptune. Its orbit, according to many models, would be highly elongated, carrying it hundreds of astronomical units from the Sun at its closest approach, and perhaps more than 1,000 astronomical units at its farthest. A single orbit could take 10,000 to 20,000 years. That is a timescale so long that it stretches the imagination. Written human history covers only a few thousand years. If Planet 9 completes one orbit every 15,000 years, then the last time it occupied the same position in space, humans were still painting on cave walls and shaping stone tools. Another interesting aspect of the simulations is the orientation of the planet's orbit. Many models suggest that it would be tilted relative to the plane in which most planets orbit, perhaps by 15 to 30 degrees. This tilt helps explain the existence of distant objects with unusual inclinations, bodies that travel on paths steeply angled compared to the familiar flat disk of the solar system. One of the remarkable things about these calculations is how sensitive they are. A slight change in the planet's mass or orbital parameters can produce very different outcomes over millions of years. Researchers run thousands of simulations, adjusting variables, comparing results, looking for combinations that reproduce the observed patterns most accurately. It is a bit like tuning an instrument. The right combination of mass, distance, and orbital shape produces a kind of gravitational harmony that matches what is seen in the outer solar system. Of course, simulations are only as good as the data that guide them. As more distant objects are discovered and their orbits measured more precisely, the models must be updated. Some simulations that once seemed promising are revised or discarded. Others gain support as new observations fit their predictions. This process is slow and methodical, but it is also deeply satisfying. There is something almost detective-like about it, following clues, testing hypotheses, refining theories, and gradually narrowing the range of possibilities. Another important factor is stability. If Planet 9 exists, its orbit must be stable over billions of years. The solar system is about 4.6 billion years old, and any large planets still present today must have survived all that time without being ejected into interstellar space or pulled into a dramatically different orbit. Simulations suggest that such stability is possible, particularly if the planet's orbit keeps it far from the giant planets most of the time. A distant, elongated orbit could allow it to remain gravitationally bound to the Sun while avoiding disruptive encounters. There is also the question of origin. If a planet of this size exists in such a distant orbit, how did it get there? One possibility is that it formed closer to the Sun and was later scattered outward during the early history of the solar system. In those early days, the giant planets may have migrated significantly, interacting with one another and with countless smaller bodies. Computer models of planetary formation often show that such interactions can fling planets into distant orbits. In some cases, those planets are ejected entirely, becoming rogue planets drifting between the stars. In other cases, they remain bound to their parent star, travelling on wide, elongated paths. Planet 9, if it exists, might be such a survivor, a planet that was pushed outward long ago but never completely escaped the Sun's gravity. Another possibility is that it formed in place, slowly accumulating material in the distant reaches of the solar system. This scenario is more challenging, because the density of material in the outer disk was likely too low to form a large planet quickly. But some researchers have suggested that under certain conditions, it might still be possible. There is even a more exotic idea that the planet was captured from another star during the Sun's early life in a stellar cluster. Stars often form in groups, relatively close together, and gravitational interactions between young planetary systems could, in principle, exchange planets. Such an event would be rare, but not impossible. At this stage, mathematics does not tell us which of these origins is correct. It simply shows that a distant planet could exist, and that such a planet could explain the observed patterns. Another interesting aspect of the modelling involves predicting where the planet might be located in the sky. By analysing the orbits of the distant objects and how they cluster, astronomers can estimate regions where the planet is more likely to be found. This does not produce a precise location, but it narrows the search area. Instead of scanning the entire sky blindly, astronomers can focus on specific regions where the probability is higher. Even so, the search remains extremely difficult. A faint, slowly moving object at hundreds of astronomical units could be easily overlooked. It might appear as a dim point of light, barely distinguishable from distant stars, shifting so slowly that its motion becomes noticeable only after months or years of observation. And yet, the history of astronomy shows that such challenges can be overcome. Neptune was found through calculations. Exoplanets were detected through subtle wobbles in starlight long before they could be imaged directly. Gravitational waves were predicted a century before instruments became sensitive enough to measure them. Mathematics often points the way long before observation catches up. There is something quietly comforting about that. The idea that the universe follows rules that can be understood, that patterns in motion can reveal unseen worlds, that patient reasoning can uncover truths hidden in darkness. At the same time, mathematics is not infallible. Models can be incomplete, assumptions can be wrong, data can be misinterpreted. The history of science includes many hypotheses that seemed promising but were later revised or abandoned. This is why astronomers continue to test the Planet 9 hypothesis from every angle, examining alternative explanations, searching for new objects, refining simulations, and improving observational techniques. The whisper of mathematics is persuasive, but it is not the final word. Still, the possibility remains compelling. A distant planet, several times the mass of Earth, travelling on a slow, elongated orbit, shaping the motions of smaller worlds through the quiet pull of gravity. A world so far from the sun that a year lasts longer than human civilization, so cold that sunlight is little more than a faint glow, and yet massive enough to leave unmistakable traces in the architecture of the solar system. If such a planet exists, what would it actually be like? Not just in terms of mass and orbit, but in terms of physical nature, composition, and appearance. Would it resemble a scaled-up Earth, rocky and solid, or a smaller version of Neptune, wrapped in thick layers of gas and ice? Would it have moons, rings, storms, or a frozen, silent surface beneath a dim and distant sun? Once astronomers began to take the possibility of a distant, unseen planet seriously, One of the first practical questions they had to consider was surprisingly straightforward. If such a world exists, how large could it be? Not just in terms of its physical diameter, but its mass, its gravity, and the role it would play in shaping the outer solar system. The answer matters, because size determines influence. A small object, even 100s of kilometers wide, simply would not have enough gravity to shape the orbits of distant bodies in a measurable way. The clustering patterns seen among extreme trans-Neptunian objects require something far more substantial, something with enough mass to gently guide those objects over millions of years. At the same time, the planet cannot be too large. If it were comparable in mass to Jupiter or Saturn, its gravitational effects would likely be far more dramatic than what we observe. It might disrupt the orbits of the giant planets themselves, or leave signatures that would already be obvious in the motions of known bodies. So astronomers began looking for a middle ground, a range of masses that could explain the observations without contradicting what we already know about the solar system. Simulations provided a useful guide. By adjusting the mass of a hypothetical planet and observing how it influenced the orbits of distant objects, researchers found that a planet between roughly 5 and 10 times the mass of Earth produced results that matched the data reasonably well. That might not sound enormous at first, but it places such a world in an interesting category. Earth is the largest of the rocky planets, but a planet 5 to 10 times its mass would likely not be rocky in the same way. Gravity at that scale tends to pull in thick layers of gas and volatile compounds during formation, producing a type of world sometimes called a mini-Neptune or super-Earth. These kinds of planets are surprisingly common around other stars. In fact, one of the most intriguing discoveries of modern astronomy is that planets slightly larger than Earth, but smaller than Neptune, appear to be among the most common types in the galaxy. Yet our own solar system seems to lack such a world in its inner regions. If Planet 9 exists, it might belong to this category, a distant cousin of Uranus or Neptune, though smaller and far colder. Estimating its physical size requires considering its likely composition. A planet 5 to 10 times Earth's mass might have a diameter 2 to 4 times that of Earth, depending on how much of it is made of rock, ice, or gas. If it formed in the outer solar system, it likely contains large amounts of water ice, methane, ammonia, and other volatile substances, along with a possible envelope of hydrogen and helium. At such great distances from the Sun, temperatures would be extremely low, perhaps around -200 degrees Celsius, or even colder. Any atmosphere would be sluggish and frigid, possibly forming layers of frozen clouds or hazes. Sunlight would be faint, more like a bright twilight than daylight as we know it. Imagining such a world can be strangely calming. The Sun would appear as a brilliant star rather than a blazing disk. Shadows, if visible at all, would be faint and soft. The sky would be dark even at midday, with distant stars visible most of the time. But size is not only about physical dimensions. Mass determines gravity, and gravity determines how strongly a planet influences its surroundings. A planet several times more massive than Earth could exert a steady gravitational pull over enormous distances, shaping the orbits of smaller bodies without needing to come close to them. This is the key to the Planet 9 hypothesis. The observed clustering of distant orbits does not require violent interactions or close encounters. It requires a persistent, gentle influence acting over millions or billions of years. Another factor to consider is brightness. Even a relatively large planet can be extremely difficult to detect if it is far enough away. The amount of sunlight reflected by a planet decreases rapidly with distance, and the light must travel all the way back to Earth, becoming fainter still. A planet several hundred astronomical units from the Sun could be thousands of times dimmer than Neptune as seen from Earth. Detecting such a faint object requires sensitive instruments and long exposures, and even then it might appear only as a tiny point of light among countless stars. There is also the matter of movement. Planets closer to the Sun move noticeably against the background stars over days or weeks. but a planet at hundreds of astronomical units would move so slowly that its motion might be detectable only over months or years. This makes it easy to overlook in surveys designed to find faster-moving objects. So a planet can be large and still remain hidden, not because it is small, but because it is distant and slow. Astronomers have also considered the possibility that Planet 9 could be slightly larger or smaller than current estimates suggest. Some models allow for masses as low as 3 Earth masses or as high as perhaps 20, though the most consistent simulations tend to cluster in the 5 to 10 range. The exact size depends on the details of the planet's orbit as well. A more massive planet could be farther away and still produce the observed effects, while a less massive one would need to be somewhat closer. This interplay between mass and distance is one of the reasons the search remains challenging. Without direct observation, astronomers must work with ranges and probabilities rather than precise values. Another interesting question is whether such a planet would have moons. Many planets in our solar system, especially the larger ones, are accompanied by satellites. If Planet 9 formed in a similar way to Uranus or Neptune, it might possess a small system of moons, perhaps captured objects from the Kuiper Belt or remnants of its formation. These moons would be even fainter and more difficult to detect than the planet itself, but their existence would not be surprising. There is also the possibility of internal heat. Even far from the Sun, planets can retain heat left over from their formation, or generated by radioactive decay. Uranus and Neptune, for example, emit more heat than they receive from the Sun. A distant planet might have a faint internal warmth, enough to drive slow atmospheric motions or maintain subsurface layers of liquid beneath thick ice, though at such extreme distances, everything would proceed very slowly. Thinking about these possibilities can change the way we imagine the solar system. Instead of ending with Neptune and a scattering of small icy bodies, it becomes a much larger and more varied system, with distant regions that may still contain substantial worlds waiting to be found. It is worth remembering that our understanding of planetary systems has expanded dramatically in recent decades. Before the discovery of exoplanets, we assumed that other planetary systems would resemble our own. Instead, we found an astonishing diversity of worlds, from hot Jupiters skimming the surfaces of their stars to planets orbiting in tight, compact systems very different from ours. This diversity reminds us that nature often produces outcomes more varied than we expect. A distant, massive planet in a wide orbit may seem unusual, but it is not beyond the realm of possibility. At the same time, astronomers remain cautious. The existence of Planet 9 is still a hypothesis, supported by intriguing evidence but not yet confirmed. Estimates of its size and mass are based on models that depend on the accuracy of the data and the assumptions built into the simulations. New discoveries could refine those estimates or even challenge the hypothesis entirely. That is the nature of science, a process of continuous testing and revision, guided by evidence. Still, the idea of a world several times the mass of Earth, moving slowly through the outer darkness, is a compelling one. It invites us to think about the solar system not as a finished map, but as a landscape still being explored, with distant horizons that may hold surprises. If such a world exists, how would it move? What would its orbit look like, and how long would it take to complete a single journey around the Sun? To picture how such a distant world would move, it helps to begin with something familiar. Earth takes 1 year to circle the Sun. That rhythm feels natural to us because it shapes everything: seasons, calendars, even the way we think about the passage of time. Mars takes almost 2 years. Jupiter takes nearly 12. Neptune, drifting in the cold outskirts compared with Earth, takes 165 years to complete a single orbit. Now imagine stretching that distance outward again and again, until the orbit becomes so large that the numbers stop feeling intuitive. A planet hundreds of astronomical units from the Sun might take 10,000, perhaps even 20,000 years to complete one journey around it. That means that since the last time such a planet was in the same part of its orbit, all of recorded human history would have unfolded, from the earliest cities to the present day, and the planet would still not have finished a single year of its own. This enormous timescale changes the way motion itself feels. In the inner solar system, planets sweep along their paths at noticeable speeds. Astronomers can track their movement from night to night. But a planet at hundreds of astronomical units moves slowly, so slowly that from our perspective, its position against the background stars would shift only slightly over many months. That slow movement is one of the reasons such a planet could remain undetected for so long. It would not reveal itself through obvious motion, and its faint reflected sunlight would make it difficult to distinguish from distant stars. It would simply drift, patient and unhurried, following an orbit that unfolds on a timescale far beyond a human lifetime. The shape of that orbit is likely not a simple circle. Most models of Planet 9 suggest an elongated path, what astronomers call a highly eccentric orbit. That means there would be times when the planet comes relatively closer to the Sun, perhaps a few hundred astronomical units away, and other times when it travels much farther, possibly 1,000 astronomical units or more. Even at its closest approach, the Sun would appear very small in the sky, more like an intense star than the broad, bright disk we see from Earth. At its farthest point, sunlight would be dimmer still, reduced to a cold glow barely strong enough to illuminate the surface. Temperatures in such an environment would be extremely low. The surface, if the planet has one beneath any atmosphere, would be colder than most places in the solar system, except for the most distant comets and dwarf planets. Any gases that require warmth to remain vapor would freeze. Methane, nitrogen, carbon monoxide, substances that form clouds or atmospheres on other worlds, might settle as frost or ice. Yet even in such cold, motion continues. Gravity does not slow down in the cold, and orbital mechanics do not depend on temperature. The planet would continue its long path, guided by the Sun's gravity, unaffected by the darkness except in appearance. There is something quietly remarkable about the persistence of motion on such scales. A planet could spend thousands of years travelling outward, slowing gradually as it climbs away from the Sun's gravitational well, then thousands more years falling back inward, accelerating again as gravity pulls it closer. The orbit would be like a slow breath, expanding and contracting over ages. During the distant part of the orbit, the planet would move at its slowest speed, lingering in the far darkness for long stretches of time. This is important, because it means that statistically, if such a planet exists, it is most likely to be found near the farthest part of its orbit. That is where it spends the greatest fraction of its time, simply because it moves more slowly there. Unfortunately, that is also where it would be faintest and hardest to detect. Another interesting aspect of such an orbit is the possibility of seasons, though they would be unlike anything familiar. Seasons depend on two main factors: the tilt of a planet's axis and its distance from the Sun. On Earth, the tilt of about 23.5 degrees creates the cycle of seasons each year. But on a planet with a year lasting 10,000 years, a single season could last thousands of years. Imagine a winter that lasts longer than recorded history, or a summer that unfolds so slowly that no civilization could observe its beginning and end. Changes in temperature, already subtle at such distances, would be gradual beyond ordinary comprehension. Of course, the extreme cold and faint sunlight mean that seasons might not have dramatic effects on the surface. The differences between winter and summer might be measured in small shifts of temperature rather than sweeping changes in climate. The tilt of the orbit itself also matters. Many models suggest that Planet 9's orbit would be inclined relative to the plane of the solar system. That means it would not travel in the same flat disk as most planets, but would rise above and dip below that plane over the course of its long journey. This inclination could help explain the existence of distant objects with unusual orbital tilts. Over millions of years, the gravitational influence of a tilted, distant planet could gradually alter the orientations of smaller bodies, nudging them into orbits that differ from the main planetary plane. It is a slow process, but slow processes are the rule in the outer solar system. There are no rapid collisions or dramatic migrations happening now, only the steady pull of gravity shaping orbits over immense spans of time. There is also the question of how such an orbit would remain stable. The solar system is not empty. The giant planets, particularly Jupiter and Saturn, exert strong gravitational influences. If a distant planet's orbit brought it too close to these giants, its path could be altered dramatically, perhaps even ejecting it from the solar system entirely. For Planet 9 to remain bound to the Sun for billions of years, its orbit would need to avoid such close encounters. Simulations suggest this is possible if the planet's closest approach remains far beyond Neptune, keeping it safely separated from the strongest gravitational perturbations. This kind of long-term stability is one of the factors researchers examine when testing different orbital models. A hypothetical planet that produces the right clustering of distant objects but becomes unstable after a few million years would not be a convincing explanation. The real solar system has endured for billions of years, so any proposed configuration must be stable over comparable timescales. Another quiet detail worth considering is how the sky would look from such a world. The sun would be bright, but not overwhelmingly so. The giant planets, if visible at all, would appear as faint stars. The Milky Way would stretch clearly across the sky, unobscured by atmospheric haze if the planet's atmosphere were thin or absent. Night and day, if the planet rotates, would still exist, but the difference between them might be subtle, especially at great distances where sunlight is already dim. The stars would dominate the sky, steady and bright, with the sun simply one among many, though still the brightest. It is easy to imagine such a world as silent, and in many ways it would be. There would be no wind unless an atmosphere existed, no flowing water, no rustling leaves. Any sound would require an atmosphere to carry it, and even then conditions would be so cold that activity would be minimal. Yet silence does not mean stillness. Beneath the surface, radioactive elements might release heat slowly, warming the interior. Tidal forces from many moons could generate additional heat, though probably weak. Geological processes might continue at a slow pace, perhaps forming cracks in icy crusts or allowing subsurface layers to remain slightly warmer than the frozen exterior. Even in the coldest parts of the solar system, change continues, only at a pace that stretches far beyond everyday experience. From our perspective on Earth, observing such a planet would require extraordinary patience. Astronomers would need to compare images of the same region of sky, taken months or years apart, looking for a faint point that shifts slightly relative to the background stars. It is meticulous work, requiring careful calibration and precise measurements. Modern surveys are improving this process. Large telescopes equipped with wide-field cameras can scan vast areas of the sky repeatedly, building up detailed maps over time. Computers analyze these images, searching for tiny movements that might indicate a distant object. Still, the search remains challenging. A planet at the far reaches of its orbit could be so faint that it lies near the limits of detection, indistinguishable from the countless distant galaxies that fill deep images of the sky. This is one of the reasons the Planet 9 hypothesis remains unconfirmed. The planet, if it exists, is not hiding deliberately. It is simply distant, faint, and slow. Qualities that make detection difficult but not impossible. There is something calming in the idea of such a world moving steadily through the darkness, unaffected by the concerns of the inner solar system, following a path set billions of years ago. It reminds us that the solar system is not a small compact place, but a vast environment extending far beyond the orbits we usually imagine. And as astronomers continue to search, refining models and scanning the sky, the question remains open. A long, cold, silent orbit may be carrying a world we have not yet seen, one that reveals itself only through the gentle pull it exerts on distant bodies. Understanding that orbit is only part of the mystery. Another question naturally follows, and it is one that many people ask when they first hear about Planet 9. If such a large world exists, why has no one seen it yet? What makes it so difficult to detect, even with modern telescopes and decades of careful observation? At first glance, the idea that a planet several times more massive than Earth could still be undiscovered in our own solar system sounds almost impossible. We live in an age of powerful telescopes, space probes, and detailed maps of distant galaxies. We have photographed planets orbiting other stars, detected gravitational waves from colliding black holes, and measured the faint glow left over from the birth of the universe itself. So how could an entire planet remain hidden so close to home? The answer becomes clearer when we remember just how large the solar system really is, and how different the outer regions are from the bright, familiar inner worlds. Distance is the first and most important factor. Light from the sun spreads out in all directions, and its intensity decreases rapidly with distance. At Neptune, sunlight is already about 900 times weaker than at Earth. At distances hundreds of astronomical units away, sunlight becomes faint to the point where a planet would reflect only a tiny amount of light back toward us. Even a large world, one perhaps several times the mass of Earth, could appear as a dim point of light, barely distinguishable from distant stars or galaxies. It would not shine brightly like Jupiter or Venus. It would not reveal details or colours. It would simply be a faint speck, lost in the enormous background of the night sky. And that night sky is far more crowded than many people realise. Modern telescopes can see millions of stars in a single region of space, along with countless distant galaxies, each one appearing as a tiny, faint dot. Searching for a single, slow-moving object among all those points of light is like looking for one drifting snowflake in a blizzard, except the snowflakes are separated by distances so vast that motion becomes difficult to detect. Motion is the second reason Planet 9 could remain unseen. Objects closer to the Sun move noticeably against the background stars over short periods. Asteroids, for example, can be tracked over hours or days because their movement is relatively rapid. But a planet hundreds of astronomical units away would move very slowly across the sky. Over a single night, its position might not change at all in any detectable way. Astronomers often rely on motion to identify solar system objects. By comparing images taken on different nights, they look for points of light that shift slightly relative to the fixed stars. A distant planet moving extremely slowly might require months or even years before its motion becomes clear. This slow pace means that many surveys, especially older ones, were not designed to detect such objects. Observations might cover a region of the sky only briefly, or images might not be compared over long enough intervals to reveal very slow movement. Another challenge is the sheer size of the search area. The sky is enormous, and although astronomers have mapped large portions of it, not all regions have been surveyed with equal depth or sensitivity. Some areas near the plane of the Milky Way are particularly difficult to study because of the dense background of stars and dust which can obscure faint objects. If Planet 9 happens to lie in one of these regions, it could be especially hard to detect. Its faint light would be lost among the crowded starfields, and distinguishing it from background objects would require careful, repeated observations. Brightness also depends on the surface or atmosphere of the planet. A world covered in bright ice might reflect more sunlight than one with a darker, more absorbing surface. If Planet 9 has a relatively low reflectivity, known as low albedo, it would appear even fainter than expected for its size and distance. There is also the possibility that the planet is currently near the farthest point of its orbit, called aphelion. As discussed earlier, objects in elongated orbit spend most of their time near this distant point, moving slowly and receiving very little sunlight. If Planet 9 is in that part of its orbit now, it would be at its faintest and most difficult to find. Another factor that makes detection difficult is temperature. A very cold planet emits little infrared radiation compared with warmer objects, Some telescopes search for distant bodies by detecting their heat rather than reflected sunlight, but a planet at extreme distances might be so cold that even its thermal emission is faint. All of these factors combine to create a situation where a large object can remain hidden, not because it is invisible in principle, but because it is faint, slow, and located in a vast region of space that has not yet been thoroughly searched. It is also worth remembering that astronomy is a relatively young science in terms of systematic sky surveys. Large digital surveys that repeatedly scan the entire sky have become common only in the past few decades. Earlier generations of astronomers relied on photographic plates and smaller fields of view, making it harder to detect very faint, slowly moving objects. Technology is improving rapidly, however. New telescopes with wide-field cameras can capture enormous areas of the sky in a single image, and advanced software can compare images taken at different times, looking for tiny changes in position or brightness. One of the most promising instruments in this search is the Vera C. Rubin Observatory, which is designed to conduct a survey of the entire visible sky repeatedly over many years. By observing the same regions again and again, it can detect objects that move very slowly, including distant trans-Neptunian objects and possibly Planet 9 itself. Even with such powerful tools, the search requires patience. Data must be processed, analysed, and verified. Candidate objects must be tracked over time to confirm their motion and determine their orbits. This is not a process that produces instant results. It unfolds gradually, often over years. There is also an important philosophical point here. The fact that we have not seen something does not necessarily mean it is not there. Throughout the history of science, many objects and phenomena remained undetected until technology improved or new methods were developed. Uranus was invisible to the naked eye as a planet and was mistaken for a star for centuries. Neptune was discovered only after mathematical predictions guided observers to the right part of the sky. Pluto itself remained unknown until the 20th century, despite being part of the solar system all along. The outer solar system is still a frontier, a region where discoveries continue to be made. Each year, astronomers identify new distant objects, refine orbital calculations, and improve our understanding of how this vast region is structured. There is something quietly humbling about this realization. Even in our own cosmic neighborhood, there are places we have not yet fully explored, objects that may be waiting just beyond the limits of our current observations. Another reason Planet 9 has not been seen may lie in expectations. For a long time, astronomers assumed that any large planet would orbit relatively close to the plane of the solar system, the flat disk in which most planets travel. If Planet 9 has a significantly tilted orbit, it could spend much of its time far above or below this plane, in regions of the sky that were not the primary focus of earlier surveys. This possibility has influenced modern search strategies. Astronomers now consider a wider range of potential locations, scanning regions that might once have seemed unlikely. As the search continues, it is important to remember that science often progresses through gradual accumulation rather than sudden revelation. Each new observation adds to a growing body of evidence, refining models and narrowing the range of possibilities. Planet 9 may be found someday, appearing as a faint moving point in a series of images, its orbit calculated and confirmed over years of observation. Or the hypothesis may eventually be ruled out, replaced by a different explanation for the observed clustering of distant objects. Either outcome would deepen our understanding of the solar system. For now, the mystery remains open, a question that continues to guide observations and inspire new research. Finding a distant world is rarely a matter of simply pointing a telescope at the sky and waiting for something to appear. The search for Planet 9, in particular, is less like looking for a bright lighthouse, and more like searching for a single firefly somewhere beyond a dark horizon, knowing only that it might be there, faint and slow, moving so gradually that its presence becomes clear only after long, careful observation. To understand how astronomers carry out such a search, it helps to think about what a telescope really does. At its simplest, a telescope gathers light. The larger the mirror, the more light it collects, and the fainter the objects it can reveal. But modern telescopes do much more than magnify distant objects. They record enormous digital images, capturing millions or even billions of points of light in a single exposure. Those images are then analysed by computers, compared over time, and studied for subtle changes that might indicate motion. In the search for Planet 9, motion is often more important than brightness. A distant planet may not stand out in a single image, but if it moves slightly against the background of stars over weeks or months, that motion becomes a clue. This means that astronomers are not only building powerful telescopes, but also designing surveys that repeatedly scan the same regions of sky, creating time-lapse records of the cosmos. Each observation adds another layer of information, another opportunity to notice something that was not obvious before. One of the most significant tools in this effort is the Vera C. Rubin Observatory, located in Chile. This observatory was designed specifically to survey the sky systematically and repeatedly, using a telescope equipped with one of the largest digital cameras ever built. Each image captures a vast area of the sky in extraordinary detail, and over the course of its survey, the observatory will photograph the entire visible sky again and again for years. This repeated coverage is crucial. A distant object that moves only a tiny fraction of a degree per year might be invisible in a single observation, but over many months its movement becomes measurable. By comparing images taken at different times, astronomers can identify objects that shift slightly relative to the background stars. The process requires patience, both human and computational. Modern surveys generate enormous amounts of data, far more than any person could examine manually. Automated software scans the images, searching for patterns, flagging candidate objects, and measuring their positions with extreme precision. Even then, confirmation takes time. A faint object detected once must be observed again and again to confirm that it is real, to rule out artifacts or transient phenomena, and to determine its orbit. Only after months or years of observations can astronomers say with confidence how such an object moves around the Sun. Another important facility in the search has been the Subaru telescope, also located in Hawaii. Subaru's wide-field camera has been used to scan large portions of the sky, particularly in regions where models suggest Planet 9 might be located. These observations are carefully planned, focusing on areas of higher probability based on simulations of orbital dynamics. This targeted approach helps narrow the search, but it does not guarantee success. The sky is vast, and even narrowing the search area still leaves an enormous region to explore. A planet at hundreds of astronomical units could be anywhere along a long arc of possible positions, its faint light blending into the background. There are also telescopes that search in infrared wavelengths, looking for the heat emitted by distant objects rather than reflected sunlight. The Wide-Field Infrared Survey Explorer, known as WISE, conducted an all-sky survey in infrared light, detecting many asteroids, comets, and brown dwarfs. Data from WISE has been analysed to look for signs of a distant planet, and while it has ruled out some possibilities, it has not yet revealed a clear candidate. Infrared searches are particularly valuable because very cold objects emit most of their energy at longer wavelengths. However, a planet as distant as Planet 9 would still be extremely cold, emitting only a faint glow that may lie near the limits of current instruments. The search also involves a kind of detective work using archival data. Astronomers often return to images taken years earlier, reanalyzing them with improved techniques. A faint object that went unnoticed before might become visible when images are stacked or processed differently. In some cases, discoveries have been made not by new observations, but by revisiting old ones with fresh eyes and better tools. This aspect of astronomy is sometimes overlooked, but it plays a vital role. The sky has been photographed many times over decades, and those images form a historical record. A distant planet might already be present in some of them, too faint or too slow-moving to have been recognised at the time. There is also an interesting challenge involving the background of stars and galaxies. When astronomers search for faint-moving objects, they must distinguish them from countless distant galaxies that appear as tiny smudges of light. Some galaxies can look almost identical to a faint planet in a single image. Only by observing motion over time can the difference be confirmed. That is why repeated observations are so important. A galaxy remains fixed relative to other distant objects, while a planet shifts slightly night after night, month after month, tracing a path that reveals its nature. Weather and atmospheric conditions add another layer of difficulty. Ground-based telescopes must contend with clouds, turbulence, and the glow of the atmosphere itself. Observations can be interrupted or delayed, and some regions of the sky may be visible only during certain times of year. Space-based telescopes avoid many of these limitations, but they have their own constraints, including limited observation time and narrower fields of view. The search for Planet 9 benefits from a combination of both approaches: ground-based surveys scanning wide areas, and space telescopes providing detailed follow-up observations. Another subtle challenge is the brightness of the Milky Way. In regions where the galaxy's dense star fields stretch across the sky, detecting faint objects becomes much harder. The background light creates noise, making it difficult to pick out a dim, slowly moving point. This means that some areas of the sky are particularly challenging to search, and if Planet 9 happens to lie in one of those regions, it could remain hidden longer, simply because the conditions make detection more difficult. Despite these challenges, progress continues steadily. Each year, new trans-Neptunian objects are discovered, their orbits calculated, their positions tracked. These discoveries refine models of the outer solar system and help narrow the possible locations where Planet 9 might be found. There is a quiet persistence to this work, a sense of patience that fits well with the slow rhythms of the outer solar system itself. Astronomers know that discovery may take years or even decades, and they are prepared for that. The search is not a race, but a careful, methodical exploration. It is also a collaborative effort involving researchers around the world. Data from one telescope may be analysed by teams in different countries, combined with observations from other instruments, and discussed in conferences and journals. The search for a distant planet is not the work of a single observer peering through an eyepiece, but a global project involving technology, computation, and shared knowledge. There is something comforting about that image. People working together quietly, night after night, gathering faint light from the edges of the solar system, piecing together clues about a world that may or may not be there. And yet, even with all this effort, the possibility remains that Planet 9 could elude detection for some time. Its orbit may place it in a region of the sky that has not yet been thoroughly surveyed, or its brightness may lie just below the sensitivity of current instruments. But new technology continues to improve our reach. Larger mirrors, more sensitive detectors, and more powerful computers all increase the chances of success. Surveys that would have been impossible a generation ago are now routine, and the pace of discovery continues to accelerate. At the same time, astronomers remain cautious. The absence of detection so far does not confirm the planet's existence, but neither does it rule it out. The search continues, guided by models, refined by new data, and driven by the quiet curiosity that has always propelled exploration. As telescopes keep scanning the sky and surveys accumulate more observations, another important question remains in the background. What if the clustering of distant orbits has a different explanation altogether? What if the patterns that seem to point toward a hidden planet could be produced by other mechanisms, perhaps involving smaller bodies, observational biases, or processes we do not yet fully understand? As intriguing as the idea of a hidden planet may be, astronomers are careful not to settle on a single explanation too quickly. Science rarely moves in straight lines, and patterns that seem convincing at first can sometimes dissolve under closer examination. When researchers began studying the clustering of distant orbits, many were excited by the possibility of Planet 9, but just as many asked a quieter, equally important question. What if the pattern has another cause? This question is not a sign of doubt in the negative sense. It is part of how science protects itself from error. Every hypothesis, no matter how appealing, must compete with other explanations. The goal is not to defend an idea, but to test it until only the most reliable explanations remain. One of the first alternative explanations involves observational bias. This is a subtle but powerful effect. Telescopes do not search the entire sky evenly. Some regions are observed more often, some less. Some surveys are better at detecting objects in certain positions or brightness ranges. Over time, these differences can influence which objects are discovered and which remain unseen. Imagine trying to understand the distribution of fish in a lake by casting a net repeatedly in only one corner. You might conclude that most fish live in that area simply because that is where you have looked most carefully. The same principle applies to astronomy. If distant objects are easier to detect in certain regions of the sky, the sample we observe may not represent the true distribution. Several research teams have examined this possibility in detail. They studied the survey methods used to discover extreme trans-Neptunian objects, analysing where telescopes were pointed, how detection sensitivity varied, and how likely it was that certain orbits would be discovered compared with others. Some studies concluded that observational bias could account for at least part of the clustering. Others argued that the clustering remained statistically significant even after these biases were considered. The debate continues, and new data from ongoing surveys are helping to refine the analysis. Another possibility is that the clustering arises not from a single large planet, but from the combined gravitational influence of many smaller bodies. The outer solar system contains countless objects, from dwarf planets to icy fragments. Over long periods, their collective gravity might influence each other in subtle ways, producing patterns that resemble the effect of a larger body. This idea is sometimes called the self-gravity hypothesis. In principle, if enough mass were distributed among many distant objects, their combined influence could shape orbital orientations. However, current estimates suggest that the total mass of known objects in the outer regions is probably too small to produce the observed effects. Still, the possibility cannot be dismissed entirely, especially since many distant bodies remain undiscovered. There is also the question of past events. The solar system did not form in isolation. In its early history, the Sun was part of a cluster of young stars all forming from the same giant cloud of gas and dust. During that time, stars passed relatively close to one another, compared with the vast distances between stars today. A close stellar encounter could have disturbed the outer solar system, pulling some objects into elongated orbits and creating patterns that persist even now. Such an event might explain the existence of objects like Sedna, whose orbit is difficult to account for through interactions with the known planets alone. If a passing star influenced the outer solar system billions of years ago, it might have left behind a population of objects with similar orbital characteristics, creating the appearance of clustering without requiring a hidden planet. Another intriguing possibility involves the migration of the giant planets. Models of the early solar system suggest that Jupiter, Saturn, Uranus, and Neptune did not form exactly where we see them today. Instead, they likely moved inward or outward over time, interacting with smaller bodies and reshaping the architecture of the solar system. This period of migration could have scattered objects into distant orbits, some of which might still retain the imprint of those early interactions. If that is the case, the clustering we observe today could be a fossil pattern, a relic of events that occurred billions of years ago rather than the influence of a planet that still exists. There is also the possibility that our understanding of orbital dynamics in the outer solar system is incomplete. The gravitational environment at such distances is subtle and complex. Small effects that are negligible closer to the Sun can become significant over millions of years. Interactions with the galactic tide, the gravitational influence of the Milky Way itself, may play a role in shaping the orbits of distant bodies. The galactic tide is an effect that arises because the solar system is embedded in the gravitational field of the galaxy. Over long timescales, this field can perturb the orbits of objects in the distant Oort cloud, and it may also influence bodies in the outer reaches of the scattered disk. While these effects are generally weak, the timescales involved are enormous. Given enough time, even a gentle force can produce noticeable changes. Some researchers have explored whether the galactic tide, combined with the gravitational influence of passing stars over billions of years, could produce patterns similar to those attributed to Planet 9. So far, most models suggest that these effects alone are unlikely to produce the specific clustering observed, but the question remains open. Another potential explanation involves statistical chance. Human minds are very good at recognizing patterns, sometimes even when those patterns are not truly significant. When dealing with small samples, coincidences can appear meaningful simply because there are not enough data points to reveal the true distribution. This is why astronomers place so much emphasis on discovering more objects. Each new observation helps clarify whether a pattern is real or merely apparent. If clustering persists as the sample grows, it becomes more convincing. If it fades, it may have been an illusion. In recent years, additional extreme trans-Neptunian objects have been discovered, and many of them appear to support the clustering hypothesis, though the sample is still relatively small. The debate continues, with researchers carefully analysing each new discovery to see how it fits into the overall picture. There is also a more unusual possibility, one that occasionally appears in scientific discussions and often captures the imagination of the public. Some have wondered whether the clustering could be caused by a massive disk of small objects, a kind of extended belt of material far beyond Neptune, whose collective gravity might influence distant orbits. While this idea is theoretically possible, it would require a large amount of mass, far more than has been observed so far. Detecting such a disk would also present challenges, but current observations do not strongly support this scenario. The presence of alternative explanations does not weaken the Planet 9 hypothesis. In fact, it strengthens the scientific process by ensuring that all possibilities are considered and tested. The goal is not to prove one idea right, but to find the explanation that best fits the evidence. There is something reassuring about this careful approach. It reminds us that science is not about rushing to conclusions, but about patiently gathering data, testing ideas, and allowing understanding to emerge gradually. For now, Planet 9 remains one of several possible explanations for the clustering of distant orbits. It is a compelling possibility, supported by simulations and consistent with many observations, but it is not yet confirmed. Alternative explanations continue to be explored, and new discoveries may shift the balance of evidence in unexpected ways. In the meantime, the outer solar system remains a place of quiet mysteries, where faint objects drift in darkness and clues accumulate slowly year by year. Each new observation adds a piece to the puzzle, bringing us a little closer to understanding what is happening at the far edge of the Sun's influence. There is another possibility that astronomers sometimes consider, one that changes the story in a rather dramatic way. Instead of imagining Planet 9 as a world that formed alongside the other planets and was later scattered outward, some researchers have wondered whether it might have formed somewhere else entirely, around another star long before the Sun ever captured it. At first, that idea might sound unlikely, almost like something from speculative fiction. Planets belong to their stars, after all. They form in disks of gas and dust that surround young suns, gradually gathering material until they become worlds. The thought of a planet leaving one star and settling into orbit around another feels unusual. But when you look more closely at how stars are born, the idea becomes less far-fetched than it seems. The Sun did not form alone in empty space. Like most stars, it was born in a cluster, a crowded stellar nursery where dozens or even hundreds of young stars formed from the same giant cloud of gas. In such environments, stars are much closer to one another than they are today. Instead of being separated by trillions of kilometers, they may pass within a few 100 billion kilometers of each other, distances that are enormous by human standards but relatively small on a cosmic scale. During those early millions of years, each young star was surrounded by a disk of material, forming planets, asteroids, and comets. Gravitational interactions between nearby stars could disturb these disks, pulling on them, reshaping them, and sometimes even capturing objects from one system into another. Computer simulations of young star clusters suggest that this kind of exchange is possible, though not common. A planet drifting in a wide orbit around one star could be nudged by a passing neighbour, its path altered just enough that it becomes gravitationally bound to the second star instead. The process is delicate, requiring the right speeds, distances, and timing, but it does not violate any laws of physics. If such an event happened in the Sun's early history, it could explain why a large planet might occupy an unusually distant and tilted orbit today. A captured planet would not necessarily follow the same orbital plane as the planets that formed from the Sun's original disk. Its path could be inclined, elongated, and somewhat irregular, reflecting the chaotic circumstances of its capture. This possibility has been explored in several studies. Researchers simulate young star clusters, allowing stars to pass near one another, and they observe how often planets might be exchanged. The results suggest that while capture is rare, it is not impossible, especially for planets that already orbit far from their original stars. There is a certain elegance to this idea. Instead of being a leftover from our own solar system's formation, Planet 9 could be an interstellar traveller, a world that spent its earliest years circling a different sun under a different sky before becoming part of our own system. Imagining such a history invites the mind to wander a little. If this planet formed elsewhere, it might have a composition slightly different from the planets that formed here. The proportions of ice, rock, and gas in protoplanetary disks vary from one star to another. A captured planet might carry chemical signatures that differ subtly from those of Uranus or Neptune, clues to a birthplace long lost. Of course, detecting such differences would require observing the planet directly, measuring its atmosphere or surface composition, which remains far beyond our current capabilities. For now, the idea remains theoretical, a possibility supported by simulations but not yet by direct evidence. Another aspect to consider is the stability of a captured orbit. When a planet is captured, its initial path is often highly elongated and inclined. Over time, gravitational interactions with other planets and the galactic environment can modify the orbit, sometimes stabilizing it, sometimes ejecting the planet entirely. For Planet 9 to remain in orbit around the Sun for billions of years, its path would need to settle into a stable configuration, avoiding close encounters with the giant planets and resisting the subtle perturbations of passing stars and the galactic tide. Simulations suggest that this kind of long-term stability is possible under certain conditions. A planet captured into a distant orbit, with a perihelion far beyond Neptune, and an aphelion extending hundreds or thousands of astronomical units outward, could remain bound to the Sun for the age of the solar system. There is also the question of how such a capture might affect the rest of the solar system. A newly captured planet could disturb the orbits of distant small bodies, scattering some and trapping others in resonances. Over millions of years, these interactions could produce patterns similar to those observed among extreme trans-Neptunian objects today. In that sense, the capture hypothesis could potentially explain not only the existence of a distant planet, but also the orbital clustering that first drew attention to the mystery. Still, this scenario faces challenges. Capturing a planet requires very specific conditions. The relative speeds of the stars must be low enough, the encounter distance close enough, and the gravitational interactions gentle enough to bind the planet without ejecting it entirely. Such events are rare, and some astronomers argue that scattering a planet outward from our own system is a more likely explanation. There is also the question of timing. The Sun's birth cluster probably dispersed after a few 100 million years as the young stars drifted apart into the galaxy. Any capture event would need to have occurred during that early period before the cluster dissolved and close stellar encounters became far less frequent. If Planet 9 is a captured world, it has been part of our solar system for billions of years, long enough that any direct evidence of its origin may have been erased by time. Yet the possibility remains intriguing, partly because it reminds us that planetary systems are not isolated islands. Stars move through the galaxy, occasionally passing near one another, exchanging material, influencing each other in subtle ways. The boundaries between systems are not always as rigid as we might imagine. There's also a broader context to consider. Astronomers have discovered many rogue planets, worlds that drift through interstellar space without orbiting any star. These planets may have been ejected from their original systems during periods of gravitational upheaval. If planets can be ejected, it follows that some might also be captured, given the right circumstances. The galaxy may contain countless such wanderers, silent and dark, travelling between the stars. The idea that one of them could have found a home in our solar system is not impossible, only rare. Thinking about this possibility adds another layer to the mystery of Planet 9. It is no longer just a question of whether a planet exists, but also of where it came from, what history it carries, and how its presence might reshape our understanding of planetary formation. There is something quietly humbling about the thought that our solar system, which often feels like a closed and self-contained environment, might include a world that was born elsewhere, a traveller from another star system that has spent billions of years circling our Sun in the deep darkness beyond Neptune. As astronomers continue to refine their models and search for new evidence, they keep this possibility in mind alongside others. The scattered planet hypothesis, the capture hypothesis, and alternative explanations for the orbital clustering all remain under consideration. The truth may turn out to be simpler than any of these ideas, or more complex than we currently imagine. That is often the way with scientific mysteries. The process of searching, testing, and refining ideas is as important as the final answer. And as we consider what Planet 9 might be, whether a native world pushed outward long ago or a captured wanderer from another star, another question begins to emerge naturally. If such a planet truly exists, what would its presence mean for our understanding of the solar system itself? How would it change the way we see the structure and history of our cosmic neighbourhood? If a distant ninth planet were finally confirmed, the discovery would not simply add another name to the list of worlds orbiting the Sun. It would reshape our understanding of the solar system in ways both subtle and profound. Maps would change, certainly, and textbooks would be rewritten, but the deeper impact would be on how we understand the history, structure, and evolution of our cosmic neighbourhood. For a long time, astronomers have described the solar system as having a fairly clear architecture. Close to the Sun lie the rocky planets. Beyond them, the giant planets dominate, surrounded by belts of debris such as the asteroid belt and the Kuiper Belt. Farther out still lies the distant Oort cloud, a vast spherical reservoir of comets extending tens of thousands of astronomical units into space. This structure appears orderly, almost layered, as though the solar system were arranged in zones. The confirmation of a large planet hundreds of astronomical units away would introduce a new and significant component to that structure, a bridge between the known planetary region and the distant cometary halo. It would mean that the planetary system does not end with Neptune, nor even with the Kuiper Belt, but extends much farther into space than most people imagine. One of the first changes would be in our understanding of planetary formation. Current models of how planets form must account for the observed arrangement of worlds. If a planet several times the mass of Earth exists in a distant elongated orbit, those models would need to explain how such a configuration arose and remained stable for billions of years. This could strengthen certain theories about the early solar system, particularly those involving planetary migration and scattering. Many simulations suggest that the giant planets moved significantly during their early history, interacting with a disk of smaller bodies and possibly with additional planets that no longer exist. If Planet 9 formed closer to the Sun and was later scattered outward, it would provide direct evidence that such dramatic rearrangements really occurred. It would be a surviving witness to a time when the solar system was far more chaotic than it appears today. Another important change would involve our understanding of the Kuiper Belt and scattered disk. The presence of a distant massive planet could explain many of the unusual orbital patterns observed among extreme trans-Neptunian objects. The clustering of their orbits, the existence of highly inclined bodies, and the stability of certain distant objects could all be seen as natural consequences of Planet 9's gravitational influence. In that sense, the outer solar system would become a more coherent system. Instead of a collection of puzzling anomalies, we would have a unifying explanation that ties many observations together. There would also be implications for the origin of long-period comets. The gravitational influence of a distant planet could alter the paths of objects in the outer solar system, sending some inward toward the Sun. This process might contribute to the supply of comets that occasionally appear in the inner solar system, adding another piece to the complex story of how material moves through our planetary system. The discovery would also affect the way we compare our solar system with others. As mentioned earlier, planets larger than Earth, but smaller than Neptune, appear to be common around other stars. Our solar system has always seemed slightly unusual in lacking such a world in the region between Earth and Neptune. If Planet 9 exists, it might fill that gap in a different way, showing that our system does contain such a planet, only in a much more distant orbit. This would bring our solar system into closer alignment with the diversity of planetary systems observed elsewhere, suggesting that certain processes of planet formation and migration may be more universal than previously thought. Another intriguing consequence would involve the definition of the solar system's boundaries. People often think of the solar system as extending to the orbit of Neptune or perhaps to the Kuiper Belt, but in reality, the Sun's gravitational influence extends far beyond that, encompassing the distant Oort cloud and even beyond. A confirmed Planet 9 would make those outer regions feel more connected to the rest of the system, less like an empty void and more like an extended, structured environment with multiple layers of objects influenced by the Sun and its planets. There would also be practical implications for future exploration. Although a planet hundreds of astronomical units away is far beyond the reach of current spacecraft, its discovery would likely inspire new ideas for missions and observations. Advances in propulsion, robotics, and remote sensing could eventually make it possible to study such a world more directly, perhaps through telescopes capable of imaging its atmosphere or detecting its thermal emission in greater detail. Even without spacecraft, improved telescopes could reveal much about its composition, temperature, and atmosphere. The study of a distant planet would provide valuable data about the physics of extremely cold environments, the behavior of ices and gases at low temperatures, and the dynamics of planetary atmospheres far from stellar heat. There is also a cultural and philosophical dimension to consider. Discoveries of new planets have always captured the human imagination. From the identification of Uranus in the 18th century to the discovery of Neptune and Pluto, each new world has expanded our sense of the solar system and our place within it. A confirmed Planet 9 would remind us that exploration is not finished, that even in our own celestial neighbourhood there are still mysteries waiting to be solved. It would be a powerful example of how science progresses, not through sudden leaps alone, but through patient observation, careful reasoning, and the willingness to question what we think we know. It would also change the way we visualize the solar system. Diagrams and models would need to be redrawn, showing a much larger scale than most familiar illustrations convey. The distances involved would become more apparent, emphasizing just how vast the region around the Sun truly is. Another subtle change would be in how we think about time in the solar system. A planet with an orbital period of 10,000 or 20,000 years introduces a different rhythm, one far slower than the cycles we usually consider. It reminds us that celestial mechanics operates on timescales that often exceed human history, and that some processes unfold so gradually that their full patterns become visible only through careful study over generations. There would also be new questions. If one distant planet exists, could there be others? Could the outer solar system contain additional massive bodies in even more distant orbits still undetected? While current evidence does not strongly support such possibilities, the discovery of one unexpected world would encourage astronomers to keep looking, to keep asking questions about what lies beyond the known frontier. At the same time, the discovery would not solve every mystery. The outer solar system would remain a complex and dynamic environment, shaped by many processes acting over billions of years. Planet 9, if it exists, would be one piece of that puzzle, albeit an important one. There is something quietly inspiring about this possibility. The idea that our solar system is still a place of discovery, that new worlds may still be found not by travelling to distant stars, but by looking more carefully at the space that surrounds us. And as astronomers consider how a ninth planet would reshape our understanding of our own system, another perspective begins to emerge. How does our solar system compare with the countless planetary systems that have been discovered around other stars? What does the possible existence of Planet 9 tell us about the diversity of planets in the galaxy and the processes that shape them? Looking beyond our own solar system can change the way we think about the possibility of Planet 9. For centuries, we had only one example of a planetary system to study, our own. Every theory about how planets form, migrate, and interact was based on a single case. It was a bit like trying to understand all forests in the world by studying only one patch of trees. That began to change in the 1990s, when astronomers started discovering planets orbiting other stars. At first, the discoveries were surprising. Some of the earliest exoplanets found were enormous gas giants, orbiting extremely close to their stars, worlds now known as hot Jupiters. These planets challenged existing theories, because our own solar system has nothing like them. As the number of discoveries grew, a more complex picture emerged. Planetary systems turned out to be extraordinarily diverse. Some stars host tightly packed systems of multiple planets, all orbiting closer to their star than Mercury is to the Sun. Others have giant planets in elongated orbits, moving far from their stars and then swinging inward again. Some systems contain planets much larger than Earth, but smaller than Neptune, often called super-Earths or mini-Neptunes, which appear to be among the most common types of planets in the galaxy. This growing catalogue of planetary systems has forced astronomers to rethink many assumptions. Our solar system, once considered typical, now appears somewhat unusual in certain ways. The absence of super-Earths in close orbits, the relatively circular paths of the giant planets, and the wide spacing between planets are not universal features. In this broader context, the possibility of Planet 9 becomes less surprising. Distant, massive planets in elongated orbits are not uncommon in other systems. In fact, observations have revealed many planets orbiting hundreds of astronomical units from their stars, detected through direct imaging or gravitational effects. These discoveries suggest that planetary systems can extend much farther than once thought, with outer regions populated by large worlds that move slowly and receive little starlight. One of the key insights from exoplanet research is that planetary migration is likely a common process. Young planets do not always remain where they form. Interactions with the protoplanetary disk with other planets or with nearby stars can alter their orbits dramatically. Some planets move inward, becoming hot Jupiters. Others move outward, settling into distant orbits. If Planet 9 exists, it might be an example of this kind of migration, a planet that formed closer to the Sun and was later scattered outward during the early history of the solar system. Similar processes are thought to occur in many other planetary systems, shaping their architecture over millions of years. Another lesson from exoplanets is that systems often contain more planets than we initially detect. Detection methods have limitations, and some planets remain hidden because they're too small, too distant, or oriented in ways that make them difficult to observe. As techniques improve, new planets are frequently discovered in systems that were once thought to contain only a few. This reminds us that our knowledge of the solar system may also be incomplete. Just as astronomers have found unexpected planets around other stars, we may still find unexpected worlds closer to home. There is also an interesting parallel involving debris disks around other stars. Many young stars are surrounded by broad belts of dust and icy material, similar to our Kuiper Belt. Observations of these disks sometimes reveal gaps, warps, or asymmetries that suggest the presence of unseen planets shaping the material through gravity. In some cases, planets have been inferred from these structures before being detected directly. The planet's gravity sculpts the disk, creating patterns that astronomers can observe even if the planet itself remains hidden. The situation with Planet 9 is somewhat similar. Instead of dust in a distant disk, astronomers are observing the orbits of icy bodies in the outer solar system. Instead of gaps or ripples in a disk, they see clustering and unusual orbital tilts. In both cases, gravity leaves signatures that can reveal unseen worlds. Another point of comparison involves orbital inclination. Many exoplanets have orbits tilted relative to the equatorial planes of their stars, sometimes even orbiting in the opposite direction of the star's rotation. These configurations suggest that planetary systems can be dynamically complex, shaped by interactions and disturbances that alter orbital planes. If Planet 9 has a significantly tilted orbit, it would fit into this broader pattern of dynamical diversity. It would show that our solar system, like others, has experienced events that disrupted the original alignment of planetary orbits. There is also the question of scale. Our solar system's known planets occupy a region extending to about 30 astronomical units from the Sun, the distance of Neptune. But exoplanet discoveries have shown that planetary systems can extend much farther. Some directly imaged exoplanets orbit hundreds of astronomical units from their stars, in environments where sunlight is faint and orbital periods are extremely long. These distant exoplan reminds us that planets can exist in regions once thought too sparse or too cold for planet formation. If such worlds are possible elsewhere, it becomes easier to imagine one existing in our own system. The discovery of Planet 9 would therefore place our solar system more firmly within the range of architectures observed in the galaxy. It would suggest that having a distant, massive planet is not unusual, but part of the natural diversity of planetary systems. At the same time, it would provide a valuable opportunity for detailed study. Exoplanets, especially those far from their stars, are difficult to observe in detail. We often know only their mass, orbit, and perhaps a few atmospheric properties. A distant planet in our own solar system, though still far away, would be much closer than any exoplanet, allowing for more precise observations over time. Studying such a world could teach us about planetary atmospheres at extremely low temperatures, the behaviour of ices and gases under faint sunlight, and the long-term evolution of planetary orbits in the outer regions of a stellar system. There is also a deeper perspective to consider. For much of history, humans viewed the solar system as a unique and orderly arrangement, a kind of cosmic standard. The discovery of exoplanets has shown that planetary systems are not uniform or predictable. They are shaped by complex histories, chance events, and interactions that produce a wide range of outcomes. Planet 9, if it exists, would be another reminder of that diversity. It would show that our own system has its own unusual features, its own history of migration, scattering, and perhaps even capture. This broader context helps place the search for Planet 9 in perspective. it is not just about finding another planet. It is about understanding how planetary systems form and evolve, how common certain configurations are, and how our solar system fits into the larger story of the galaxy. Progress in astronomy rarely happens in sudden leaps. From the outside, discoveries can look dramatic, a headline announcing a new planet, a new comet, a new signal from the depths of space. Yet those moments usually rest on years, sometimes decades, of quiet work that unfolds almost invisibly. Observations are repeated, measurements refined, theories adjusted, and small pieces of evidence slowly accumulate until, almost without anyone noticing exactly when it happened, the picture becomes clear enough to recognize. The search for a distant planet in the outer solar system is a perfect example of this slow, deliberate process. There was no single night when the mystery appeared fully formed. Instead, it began with scattered observations of faint objects, each one studied for its own sake, each orbit calculated carefully, each discovery added to a growing archive of knowledge. Only later did astronomers begin to notice that some of those orbits seemed to share unusual characteristics. Even then, recognition did not come immediately. Patterns in nature often hide in plain sight until enough data exists for them to stand out. Early discoveries of distant trans-Neptunian objects were too few to reveal a clear trend. A handful of unusual orbits might mean nothing. It is only when the sample grows larger and when measurements become more precise that subtle regularities begin to emerge. This is one reason astronomy moves slowly. The universe operates on timescales far longer than human experience. A distant object may take centuries or millennia to complete an orbit, and we observe only a small fraction of that journey. Determining an accurate orbit requires repeated observations over many years. Each new measurement refines the calculation, narrowing uncertainties little by little. There is something almost meditative about this process. Night after night, telescopes collect faint light from the sky. Images are stored, catalogued, compared. Small shifts in position are measured, sometimes amounting to only a fraction of a pixel on a digital detector. The work demands patience, attention, and a willingness to accept that meaningful results may take a long time to appear. Astronomers are accustomed to this pace. Many of the most important discoveries in the field unfolded over decades. Neptune, for example, was not discovered overnight. Its existence was inferred from small discrepancies in Uranus's orbit, discrepancies that required years of observation and calculation to understand. Even after predictions were made, the search itself required careful work, examining star fields methodically until the planet was finally identified. More recently, the detection of gravitational waves followed a similar pattern. The idea was proposed in the early 20th century. Instruments were developed and refined for decades, and only in 2015 did the first direct detection occur. The announcement seemed sudden, but it rested on generations of effort. The search for Planet 9 belongs to this same tradition. The hypothesis emerged gradually, based on data collected over many years. Simulations were run, debated, improved. Observations continued, adding new objects to the sample, testing whether the patterns held or faded. One of the challenges in such work is uncertainty. Early evidence is rarely definitive. Measurements have margins of error. Samples are incomplete. Alternative explanations remain possible. Scientists must learn to live with these uncertainties, to work within them, to refine their understanding step by step. This can be frustrating for those who hope for quick answers, but it is also what makes scientific knowledge reliable. Ideas are tested repeatedly, challenged from different angles, and supported by multiple lines of evidence before they are widely accepted. In the case of Planet 9, the process is still unfolding. Astronomers continue to discover new distant objects, each one providing another data point. Some support the clustering hypothesis, others introduce complications or raise new questions. The picture evolves gradually, becoming clearer but never entirely fixed. Technology plays an important role in this progress, but even the most advanced instruments cannot eliminate the need for time. A telescope may detect a faint object in a single night, but confirming its orbit may require years of follow-up observations. A survey may cover the entire sky, but analysing the data and verifying candidate detections is a slow, careful process. There is also the human element. Astronomy is a collaborative science involving researchers from many countries, institutions and backgrounds. Data are shared, results are discussed, interpretations are debated, papers are written, reviewed, and sometimes challenged. This dialogue is essential, but it also takes time. Ideas mature through discussion and criticism. A hypothesis becomes stronger when it survives scrutiny, when alternative explanations are considered and tested, when predictions are confirmed by new observations. Another aspect of the slow pace of discovery is the sheer scale of the universe. The outer solar system alone is vast beyond everyday comprehension. Even travelling at the speed of light, it takes hours for sunlight to reach distances where some of these distant objects travel. Observing such regions from Earth is like trying to map a coastline from across an ocean, relying on faint reflections and subtle movements. Because of this scale, progress often comes in small increments. A new object is discovered, its orbit is calculated. Months later, another object is found. Over years, patterns begin to appear. Each step is modest, but together they build a foundation of understanding. There is a quiet satisfaction in this kind of work, a sense of participating in a long tradition of exploration. Astronomers know that they are contributing to a body of knowledge that will continue to grow long after their own observations are complete. The data they collect today may be analysed by future researchers with better tools and new perspectives, revealing patterns that are not yet visible. This continuity across generations is one of the most remarkable aspects of science. Observations made decades or even centuries ago remain valuable, forming part of a record that stretches back through time. In astronomy, where processes unfold slowly, this long-term record is especially important. Consider the discovery of Pluto. Clyde Tombaug's careful examination of photographic plates in 1930 was only the beginning. Observations continued for decades, refining measurements of Pluto's orbit and size. Later, new instruments revealed its moons, its atmosphere, and eventually, through the New Horizons mission, its surface in extraordinary detail. What began as a faint point of light became a complex, richly studied world, but only through sustained effort over many years. The same pattern may unfold with Planet 9, if it exists. The first detection might be only a faint moving dot in a series of images. Confirmation of its orbit could take years. Understanding its composition and structure might require decades of observation with increasingly powerful telescopes. This gradual unfolding does not diminish the excitement of discovery. In some ways, it enhances it, allowing anticipation to build, allowing understanding to deepen step by step. There is also a philosophical dimension to the slow pace of astronomy. It reminds us that the universe does not move at human speed. Stars evolve over millions or billions of years. Galaxies collide over timescales longer than the existence of our species. Even the orbits of distant planets unfold so slowly that a single human lifetime captures only a brief moment in their history. Recognizing this can be calming in a way. It places our own sense of urgency into a larger perspective. The universe is patient, and understanding it requires patience as well. This patience is not passive, it is active, attentive, and deliberate. Astronomers design surveys, build instruments, analyze data, and refine models, all while knowing that the answers they seek may take years to emerge. The search for Planet 9 continues in this spirit. Telescopes scan the sky, data accumulate, models are updated. The evidence grows, slowly, almost imperceptibly, like the gradual brightening of dawn. and whether the hypothesis is confirmed or eventually set aside, the process itself enriches our understanding. Each observation teaches us more about the outer solar system, about the behaviour of distant objects, about the subtle interplay of gravity over immense distances. In this way, even the search itself is a kind of discovery. As we reflect on this slow, patient process, another thought begins to take shape, one that moves beyond the technical details of telescopes and simulations. The search for a distant planet is not only a scientific endeavour, but also a human one, shaped by curiosity, imagination, and the desire to understand our place in the universe. That brings us naturally to a quieter question, one that is less about the mechanics of orbits and more about the meaning of the search itself. What does it mean to look for something that may or may not be there, to spend years pursuing a possibility, guided by hints and patterns rather than certainty? There is a particular feeling that comes with searching for something that may or may not exist. It is different from looking for a misplaced object in a familiar room, where you know the thing is there somewhere, waiting to be found. It is also different from observing something already known, like tracking a planet whose orbit has been calculated and confirmed. Searching without certainty occupies a quieter space, one filled not with answers, but with possibilities. Astronomy has always lived in that space. For most of human history, people looked at the night sky without knowing what stars really were, without understanding the vast distances involved, without knowing whether other worlds existed at all. Questions came first, then hypotheses, then observations, and only gradually did understanding take shape. The search for a distant, unseen planet belongs to that same tradition, a process guided not by certainty, but by careful reasoning and patient curiosity. It is easy to imagine science as a collection of facts, neat and finished, arranged in textbooks and diagrams, but the reality is more fluid. Much of science exists in a state of uncertainty, where evidence suggests possibilities but does not yet deliver final answers. Researchers learn to work within that uncertainty, to measure it, to refine it, and sometimes to accept that it may remain unresolved for years. In the case of Planet 9, astronomers are following a trail of clues rather than a clear path. They see patterns in distant orbits. They test models that might explain those patterns. They search the sky for confirmation. At every step, they remain aware that the explanation might change, that new data might reveal a different picture, that the planet they seek might exist or might not. This willingness to pursue a question without knowing the outcome is one of the quiet strengths of science. It requires patience, but also a kind of humility, an acceptance that the universe is not obligated to match our expectations. There is something calming about that perspective. It reminds us that uncertainty is not a failure of knowledge, but a natural stage in the process of understanding. The boundary between the known and the unknown is not a sharp line, but a wide, gradual transition, where ideas are tested, revised, and sometimes replaced. Searching without certainty also changes the way we think about time. When astronomers study distant objects, they often work on timescales that extend far beyond individual careers. A survey may take a decade to complete. An orbit may take centuries to measure precisely. The full implications of a discovery may unfold over generations. In this sense, the search for Planet 9 is not the work of a single person, or even a single generation. It is part of a longer conversation, one that began with the discovery of the first trans-Neptunian objects and will continue as new telescopes and new observers add their own pieces to the puzzle. This continuity is one of the most remarkable aspects of astronomy. Observations made long ago remain valuable, forming part of a record that stretches across decades and centuries. The sky changes slowly, and so the data collected today may still be useful many years from now, helping future astronomers answer questions we have not yet fully asked. There is also a deeper human element in this kind of search. Curiosity is a quiet but persistent force. It is the reason people have always looked beyond the horizon, crossed oceans, climbed mountains, and studied the stars. The desire to know what lies beyond the edge of the map is not driven only by practical needs. It is driven by something more subtle, a sense of wonder, a feeling that understanding the universe is part of understanding ourselves. Searching for a distant planet might seem abstract compared with exploring a new continent or walking on the moon, but it arises from the same impulse. It is an extension of the same long story of exploration, carried out not with ships or rockets, but with telescopes and equations. And unlike many forms of exploration, astronomy often requires accepting that answers may not come quickly. The universe does not reveal its secrets on demand. Observations must be made when conditions allow. Data must be analysed carefully. Conclusions must be tested and retested. This slow pace can be frustrating, but it also has a certain gentleness to it. It encourages patience, reflection, and a sense of perspective. It reminds us that not everything needs to be solved immediately, that some questions are worth living with for a while. There is another aspect of searching without certainty that is easy to overlook. The process itself often leads to unexpected discoveries. While looking for one thing, scientists frequently find something else, new objects, new patterns, new phenomena that would never have been noticed otherwise. The search for Planet 9 has already produced many such discoveries. Dozens of distant trans-Neptunian objects have been found and studied, expanding our understanding of the outer solar system. Each new object adds to the map, revealing structures and dynamics that were unknown a generation ago. In this way, even if Planet 9 were never found, the search would still have been worthwhile. It would still have deepened our knowledge, still have revealed new worlds, still have taught us more about the architecture of our solar system. This is another quiet truth about science. The value of a question is not measured only by the answer it produces. Sometimes the journey itself, the observations made, the ideas tested, the new methods developed, is just as important. There is also something reassuring in the fact that uncertainty remains. It means that the universe is not fully mapped, that there are still mysteries close to home, that the story of exploration is not finished. In an age when so much of the world has been measured and catalogued, it is comforting to know that there are still questions waiting patiently in the darkness beyond Neptune. And perhaps there is a broader lesson here, one that extends beyond astronomy. Searching without certainty is not limited to science. It is part of many human experiences, learning, creating, exploring, even simply trying to understand the world around us. We often move forward without knowing exactly where the path will lead, guided by hints, by intuition, by the quiet belief that understanding is worth pursuing even when the outcome is unclear. Astronomy provides a gentle reminder of this. The sky does not hurry. Stars rise and set, planets move slowly along their paths, and distant worlds drift in silence, indifferent to our questions yet inviting them all the same. When astronomers point their telescopes toward the outer solar system, they are not just looking for a planet. They are participating in a process that stretches back centuries, the gradual expansion of human knowledge, the patient exploration of the unknown. And there is a certain beauty in that patience. The idea that understanding can grow slowly, that it can unfold over time, that it does not need to be rushed. In a world that often moves very quickly, the slow rhythms of astronomy offer a different kind of perspective, one that encourages quiet reflection. As we consider what it means to search without certainty, it becomes clear that the question of Planet 9 is not only about whether a distant world exists, it is also about how we approach the unknown, how we balance curiosity with skepticism, how we continue to explore even when answers remain just out of reach. Eventually, one of two things will happen. Either the evidence will grow strong enough that a faint moving point of light will be recognized as a new planet, its orbit confirmed, its properties studied, its place in the solar system finally understood, or the evidence will lead in another direction, revealing a different explanation for the patterns we observe, and the idea of Planet 9 will become a stepping stone toward a deeper understanding of the outer solar system. Both outcomes are valuable. Both expand our knowledge. Both remind us that science is not a collection of fixed truths, but a living process, always evolving, always refining its picture of the universe. For now, the question remains open, and perhaps that is part of what makes it so compelling. A distant region of space, faint objects moving slowly, subtle gravitational patterns, and the possibility, just beyond the limits of current observation, that a world still waits to be found. Now, after travelling so far in thought, it can be calming to return to something simple. Imagine stepping outside on a clear night, or picturing it if the sky above you is cloudy or bright with city lights. The air is cool, the world is quieter than it was a few hours ago, and above you the sky stretches outward in every direction, deeper than it first appears. At a glance, it looks peaceful and unchanging. The familiar stars are there, steady and distant. Perhaps you can pick out a constellation or two, patterns that people have recognised for thousands of years. To the eye, nothing seems to move. The sky appears still. But as we now know, that stillness is only an illusion. Every point of light is in motion. Planets are circling the sun, asteroids are drifting, distant stars are travelling through the galaxy, and far beyond Neptune, small icy worlds are tracing enormous paths that take centuries or millennia to complete. And somewhere out there, perhaps, a larger world may be moving as well, too faint to see, too slow to notice directly, but present all the same, shaping the motions of smaller bodies through the quiet pull of gravity. It is a gentle thought, not dramatic or urgent, simply the possibility that our solar system is slightly larger, slightly more complex, and slightly more mysterious than we once believed. When astronomers search for Planet 9, they are not searching with the expectation of certainty. They are following clues, testing ideas, and letting the evidence guide them wherever it leads. Sometimes that process confirms a hypothesis. Sometimes it reveals that the truth lies elsewhere. Either way, the search itself adds to our understanding. There is something reassuring in that. Knowledge does not always arrive as a sudden revelation. Often it grows gradually, like the slow brightening of dawn, so subtle at first that you do not notice it, until the landscape around you begins to take shape. The night sky invites this kind of patience. It does not rush. Stars rise and set at their own pace. The moon changes slowly from one phase to the next. Planets drift against the background of constellations over weeks and months, movements that were carefully recorded by observers long before telescopes existed. Even now, with all our technology, we are still learning to see more clearly, to measure more precisely, to notice patterns that were invisible before. The search for Planet 9 is part of that long tradition of watching and waiting. It reminds us that discovery is not always about travelling to distant places. Sometimes it is about looking more carefully at what is already around us, about noticing small details, about asking questions that no one thought to ask before. And it also reminds us of the scale of the solar system itself. It is easy to think of it as a compact arrangement of planets, neatly spaced, familiar from diagrams in books, but in reality it is vast beyond everyday comprehension. Neptune alone orbits 30 times farther from the Sun than Earth does. The Kuiper Belt extends farther still, and beyond that lies a region so distant and sparsely explored that entire worlds could remain unseen for decades. When you think about that scale, the idea of an undiscovered planet no longer feels impossible. It feels like a reminder that exploration is not finished, that there are still places to learn about, even in our own cosmic neighbourhood. At the same time, it is worth remembering that uncertainty is not a gap in knowledge that must be filled immediately. It is a natural part of understanding. Questions lead to investigations. Investigations lead to new questions, and the process continues, slowly but steadily. Astronomers are comfortable with that pace. They know that the universe reveals its patterns gradually, and that patience is often the most valuable tool they have. Perhaps there is something we can take from that in our own lives as well. Not everything needs to be solved at once. Not every question needs an immediate answer. Some things become clearer only with time, with observation, with quiet attention. If Planet 9 exists, it will eventually be found. The sky is being surveyed more thoroughly each year. New telescopes are coming online, more sensitive than any before. Data are being collected, analysed, compared. The faintest motions are being tracked with increasing precision, and if it does not exist, that answer will emerge as well through the same patient process as alternative explanations are tested and evidence accumulates. Either way, the story continues. It is comforting to think of science not as a race to reach a final answer, but as an ongoing conversation, one that stretches across generations. Observations made today will be studied by researchers years from now. Questions asked now will lead to discoveries later, sometimes in ways we cannot yet predict. And the sky itself will remain, quiet and vast, waiting to be observed. If you imagine looking upward again, you might picture the sun far away, surrounded by the familiar planets, and beyond them the distant belt of icy bodies, and beyond that the darkness where the light grows faint. Somewhere in that darkness, a world may be moving slowly along its path, taking thousands of years to complete a single orbit, untouched by the noise and activity of the inner solar system. It would not be a dramatic place, not a world of bright sunlight or roaring storms visible from afar. It would be quiet, cold and patient, like the outer solar system itself. And perhaps that is part of what makes the idea so fascinating. Not because it is spectacular, but because it is subtle, a reminder that even in the most familiar parts of the universe, there are still mysteries waiting quietly to be understood. As the night deepens, the stars seem steadier, the world a little calmer. The questions we have been exploring drift gently in the mind, not demanding answers, simply existing, like distant lights in the sky. Is there a ninth planet, moving silently beyond Neptune? The truth is that we do not yet know. But the search continues, guided by curiosity, by careful observation, and by the quiet confidence that understanding grows, step by step, even when the path ahead is not fully clear. And somewhere above, whether we see it or not, the solar system continues its slow, graceful motion, planets circling, comets drifting, distant objects tracing enormous arcs through darkness, all of it unfolding at a pace so gentle that it invites us, if only for a moment, to slow down with it, to rest in the quiet, and to let the mind wander among the stars.